For as long as we've looked up at the night sky, the moon has watched us back, silent, ancient, and full of secrets. In November 1969, something extraordinary unfolded on the lunar surface, an event that continues to provoke fascination more than half a century later. During the Apollo 12 mission, NASA astronauts made a deliberate decision to crash the lunar module's ascent stage into the moon after rejoining the command module in orbit. When the impact occurred, the seismometers left behind recorded something entirely unexpected. The moon seemed to ring. Not literally, like a bell for sound cannot travel through the vacuum of space, but the seismic reverberations were real and unmistakable. According to the data, the moon vibrated for more than 55 minutes. Engineers at NASA described it in a single unforgettable phrase: the moon rang like a bell. That sentence alone ignited decades of curiosity, research, and speculation. What could it possibly mean for the moon to ring? To grasp why this was so extraordinary, we need to recall how seismic activity behaves here on Earth. When an earthquake strikes, the vibrations travel through layers of crust, mantle, and core. Depending on what those layers are made of, the waves might speed up, slow down, scatter, or fade away. The Earth's molten, ever-shifting interior dampens seismic waves very quickly. But on the moon, something profoundly different happened. The vibrations did not fade, they persisted. For almost an hour, the echoes coursed through the lunar body with surprising uniformity. This suggested that the moon's interior was unlike Earth's. It did not act like a geologically active world with a molten core. Instead, it behaved as though it were a vast, rigid mass, or even hollow. The idea of a hollow moon might sound like something from science fiction, and indeed, no credible scientific theory supports the notion of a truly hollow satellite. Yet at that time, NASA scientists were forced to take the data seriously. Some early lunar models proposed that the moon might contain a small or partially molten core. Others suggested it had solidified completely. But the bell-like resonance pointed toward a structure that lacked internal damping, a body with no molten center to absorb energy, and a crust that was astonishingly dry and dense. Further Apollo missions confirmed the pattern. Lunar quakes behaved very differently from those on Earth. They lasted longer, traveled farther, and often began in regions unrelated to tectonic fault zones. Could the moon really be a hollow shell? Almost certainly not. But the evidence forced scientists to reconsider what they believed about its composition. The mystery deepened with Apollo 13. Though it never landed, it contributed a crucial piece to the puzzle. In April 1970, NASA directed the empty upper stage of the Saturn IVB rocket to crash into the lunar surface, with the force equivalent to 11 tons of trinitrotoluene. Seismometers once again captured the aftermath. This time the moon rang for more than 3 hours. Imagine that, 3 full hours of measurable vibration, with some frequencies continuing for over 8 hours. The waves did not simply bounce and fade. They built, resonated, and slowly diminished in a way that astonished scientists. It was as if someone had struck an immense crystal, producing a pure, sustained tone rather than a chaotic shatter. Geophysicist Dr. Clive R. Neal would later remark, "The moon was ringing like a bell." The implications were profound and not easily explained. What truly lies within the moon? To move beyond speculation, modern missions have given us clear answers. Data from NASA's Gravity Recovery and Interior Laboratory, or GRAIL mission, now paints a much more detailed and revealing picture of the moon's interior. The moon's crust stretches about 50 kilometers deep on average, lying above a mantle that is partly molten and divided into layers of varying stiffness. Beneath that, there is a solid inner core and a liquid outer core, though both are far smaller than Earth's. But here is what makes it fascinating. The moon is astonishingly dry and less dense than Earth, and that changes the way seismic waves move. Without liquid water or molten rock to absorb and scatter the vibrations, the waves continue to bounce through its body, clean and clear, producing that ghostly ringing that once caught everyone's imagination. Unlike Earth, the moon has no tectonic plates shifting beneath its surface. There is no subduction, no mid-ocean ridge, no restless crust in motion. Instead, its surface is ancient, cold, heavy, and scarred by billions of years of asteroid collisions. So when an impact or a moonquake strikes, the energy ripples through this rigid, echo-friendly crust. It is not hollow. It is simply dry, fragile, and eerily resonant. Yet the image of a ringing bell has lingered. Even as science advanced and models improved, the metaphor remained. To some, it became a spark for speculation. Fringe theories proposed that the moon was artificial, perhaps a hollow, alien base placed in orbit to watch over Earth, or a vast space station sheathed in rock. None of that stands up to evidence, but the bell-like ringing joined the catalogue of cosmic curiosities, stories that live beside talk of unidentified flying objects or imagined pyramids on Mars. And to be fair, the moon does hold its share of mysteries. Its size, orbit, tidal lock, and possible origin all defy simple explanation. The ringing is merely the first hint that something deeper may lie beneath the surface. So why should we still care that the moon rings? It is not just a quirk of physics. This phenomenon reveals how worlds form and evolve. The motion of seismic waves through a planetary body tells us about its birth, its history, and its hidden structure. Earthquakes opened a window into Earth's core. Moonquakes are now doing the same for our nearest neighbour. Studying the moon's interior helps us learn whether it once had a magnetic dynamo, how collisions shaped it in the early solar system, and what materials might be buried under its crust. It even matters for planning future lunar bases where quakes could affect construction. Each time a moonquake or impact pulse is recorded, we uncover more of the moon's unseen architecture, and sometimes those lessons quite literally sound like bells. So is the moon still ringing today? Not in a literal sense, but the mystery endures. As humanity prepares to return through NASA's Artemis program, scientists are designing new seismic experiments with modern tools and broader reach. The moon may still hold hidden truths. And if, when something strikes its surface again, that resonant echo returns, we will be listening. For something that gazes down on us nearly every night, the moon remains astonishingly enigmatic. You might assume that by now scientists would agree on how it formed, but they do not. The moon's origin is still one of planetary science's most fiercely debated puzzles. Every time a theory seems to fit, new discoveries tear it apart. The truth is, we do not yet know exactly where the moon came from. There are hypotheses, computer models, and simulations, but each carries its own flaws, and the more we learn, the more profound the mystery becomes. The leading explanation, the one printed in textbooks and documentaries alike, is known as the giant impact hypothesis. It suggests that over 4 billion years ago, a body roughly the size of Mars collided with the young Earth. This planet-sized impactor, sometimes called Theia, struck with such ferocity that debris was hurled into orbit. Over time, that debris gathered into a disk and eventually coalesced into the moon. It is a grand and dramatic vision, and for a while it seemed to account for much. The moon's lack of a dense iron core made sense. It would have formed mostly from the outer layers of Earth and Theia, not from their iron-rich hearts. Its smaller size and its current distance matched computer simulations, and the physics checked out. Such a collision could indeed have launched enough material to create a moon. But then came the complications. When the Apollo astronauts brought back samples of lunar rock, scientists compared them to those from Earth, and what they discovered was astonishing. Their compositions were almost identical. Same isotopes of oxygen, identical ratios of the essential elements, almost a perfect chemical reflection. That should not be possible. If the moon had been forged partly from another planet Theia, its rocks would bear different traces, unique isotopic fingerprints, a distinct chemical voice, yet that difference is absent. It is as if the moon is sculpted entirely from the Earth itself. This is where the first fracture appears in the giant impact theory. The chemistry refuses to fit the narrative. To mend the gap, scientists began to reshape the collision model. Perhaps Theia possessed the same isotopic identity as Earth. Perhaps the violent impact mixed the two worlds so completely that any difference was erased. Perhaps the young Earth spun so rapidly that it cast more of itself into orbit. These adjustments are ingenious, but they stir up even deeper questions. What are the odds that two planets born in different corners of the solar system could share such an astonishingly identical chemical composition? Possible, yes, but not very likely. And even if the blending was that absolute, why does the moon's chemistry still align so precisely with Earth's mantle instead of forming a more chaotic mixture? This uncertainty drove scientists to explore other explanations, one being the co-formation theory. This idea proposes that Earth and the moon emerge side by side from the same swirling disk of material encircling the young sun, two celestial twins growing together. That would account for their shared chemistry. They would indeed be made from the same cosmic dust. But then we meet another problem, the question of angular momentum. If Earth and the moon had been born together, their motions and orbits today should not look the way they do. The moon's size, its distance, its graceful motion around Earth, none of it fits the equations. The numbers refuse to cooperate. So came another hypothesis, the capture theory. According to it, the moon formed elsewhere and was later ensnared by Earth's gravity. That might explain why our moon seems so different compared with other moons across the solar system. It is remarkably large for a satellite, far larger in proportion to its planet than most others. Perhaps it wandered through the early solar system until Earth's gravity caught it. But capturing an object that massive without it either crashing into Earth or escaping back into space is incredibly difficult. Gravity is not gentle. It does not neatly lift huge bodies into stable orbits. You would need a near-perfect alignment of events, a braking mechanism, a delicate transfer of energy. We find no evidence of that in the Earth-Moon system. It would be like throwing a baseball from a moving car and watching it fall into a flawless orbit around a streetlight. Not impossible, but profoundly improbable. Other ideas venture even further. Some suggest the moon formed not from a single cataclysmic strike, but from several smaller impacts over time. Others propose that Earth once had multiple moons that slowly merged into one. There are even hypotheses of molten vapor clouds and glowing droplets condensing into a sphere in orbit. Yet none of these possibilities fully resolve the mystery. Each collides with some barrier in physics, chemistry, or timing. None can completely recreate the moon we observe today. And then there are the strange coincidences, the peculiar features that resist tidy explanations. The moon's orbit, for instance, positions it at precisely the right distance to appear the same size as the sun in our sky, making total solar eclipses possible. Such precision feels almost uncanny and has fueled myths and conspiracies alike. The moon is also unusually large in comparison with Earth, and forever shows us only one face locked in a perfect synchronous rotation. Some researchers view these as inevitable consequences of gravity and tidal forces. Others sense something deeper, something still unseen. The truth is, we do not yet know how the moon came to be. The giant impact hypothesis remains our strongest model, but it is far from complete. The chemical similarity to Earth is too precise, the physical parameters too fine-tuned. With every new lunar rock we study, every spacecraft that circles the moon, every simulation we run, the story grows more intricate. This is one of those rare scientific enigmas where the closer we look, the more uncertain we become. The moon hangs above us, quiet and patient as it always has, yet its birth remains unwritten, and that gap in our understanding is more than a missing detail. It is a profound reminder that even here, in our own cosmic neighborhood, mysteries endure. If we cannot fully explain the moon, then how much do we truly grasp about the creation of worlds themselves? The moon may seem eternal, a fixture in our sky, marking the rhythm of tides, calendars, and human dreams. But it is not fixed. It is still moving, still changing, just as our understanding of it continues to evolve. In truth, it is slipping away from us, little by little. Each year, almost imperceptibly, the moon drifts farther from the Earth, inch by inch. And although that may sound trivial, this slow retreat produces measurable and rather extraordinary consequences, ones that reach into the very fabric of time itself. This is not a poetic metaphor about perception. It is real and physical. The moon is subtly stretching the length of Earth's day, lengthening it slowly yet without pause. At this moment, the moon is moving away at roughly 3.8 centimeters every year, about the same pace at which your fingernails grow. It does not seem much, but across millions and billions of years, that gentle retreat transforms into something immense. To grasp this process, we must look toward the tides. Not the simple rise and fall of waves upon the shore, but the gravitational ballet that drives them. The pull of the moon's gravity tugs on the oceans, raising great bulges of water. Yet these bulges do not align perfectly beneath the moon, because Earth is spinning. Instead, the rotation of our planet drags them slightly ahead of the moon's orbit. That forward tilt exerts a backward pull on the moon, giving it a faint, steady push of energy. In response, the moon tugs back on Earth, gently slowing its rotation. This process, called tidal friction, is invisible and constant, and it's been shaping our world for billions of years. As a result, Earth's rotation continues to slow, which means that each day grows a fraction longer, barely noticeable yet inevitable. Today we add about 1.7 milliseconds to the length of a day every century. Long ago, Earth spun faster. Hundreds of millions of years in the past, a day lasted only 22 hours. Travel back 1.4 billion years and a day would have been just 18 hours long. The moon was nearer then, about 341,000 kilometers away, instead of the roughly 384,400 kilometers that separate us now. To our ancient ancestors, the moon would have filled far more of the sky, glowing larger and brighter. The tides then would have been ferocious, surging and crashing across coastlines with incredible power. Today, using laser reflectors placed on the lunar surface by the Apollo missions, scientists can measure the moon's distance with centimeter precision. By sending beams of light to those mirrors and timing their return, researchers have confirmed that the moon is indeed drifting away and that Earth's spin is slowing, exactly as tidal theory predicts. This delicate connection between the moon and the length of our day is among the most subtle yet profound relationships in the entire solar system. The moon is not a silent companion circling our planet. It is actively sculpting the flow of time itself. But the story does not end here. This is not merely about the past or present, it extends into the far future. If nothing disrupts the system, no cataclysmic events, no major outside forces, then eventually Earth and the moon will become tidally locked to one another. That would mean one side of Earth forever faces the moon, just as one lunar hemisphere always faces Earth today. The length of a day on our planet would grow to match the moon's orbital period, roughly 47 days. The concept of day and night as we know it would disappear. There would be no sunrise or sunset every 24 hours, no familiar rhythm of light and dark. Life, if it still existed, would unfold in a world utterly transformed. Of course, such an era lies billions of years ahead, and long before that, the sun will swell into a red giant, consuming both Earth and the moon. Yet the principle remains: this celestial system is not static, it is evolving. The moon is gently rewriting the tempo of Earth, almost imperceptibly, but with consequences that echo through geological time. There is, however, a curious twist. Some scientists suspect that the moon's recession has not always been smooth and steady. Evidence from rock strata and ancient fossils suggests that tidal patterns have shifted more abruptly at certain times in Earth's history than tidal theory alone would predict. It may be that the rate of the moon's retreat changes over time, influenced by the shape of the continents, the depth of the oceans, and the great cycles of glaciation. In this way, the geography of Earth may determine how efficiently tidal energy transfers between planet and satellite. It is not a simple one-way interaction, but a vast feedback system linking land, sea, sky, and the progression of time itself. The moon's slow outward drift also affects the mechanics of Earth's orbit and even its climate. Without the moon's steadying gravitational influence, Earth's axial tilt would fluctuate dramatically. At present, that tilt remains within a narrow band, preserving the balance of our seasons. But if the moon continues its retreat, or one day were gone entirely, the planet's tilt could begin to wobble unpredictably. The stability that allows life to flourish could unravel. In the quiet pull between Earth and its moon lies the story of time motion and the fragile equilibrium that defines our place in the cosmos. Some simulations propose that the planet's tilt could one day vary from almost 0 degrees to more than 60. Such swings would wreak havoc on global climates, on the balance of ecosystems, and on every fragile condition that allows life to exist. And here's the astonishing part. The steady rhythm of time, as we experience it today, depends entirely on this fragile cosmic dance. The reason we have 24-hour days and predictable seasons is no accident. It's the product of a gravitational partnership that began 4.5 billion years ago and continues even now. The moon has acted as our silent metronome since long before any form of humanity appeared. Without it, the notion of a day would lose all meaning. So when you gaze up at the moon, remember that it's retreating inch by inch, unseen yet relentless. As it drifts away, it's stretching Earth's days by a single millisecond at a time. Across one lifetime that's invisible, but across epochs it reshapes the very tempo of history. The moon is drifting. Time itself is bending. Even the length of a day is not the constant we imagine. There's something haunting about watching the moon cover the sun during a total solar eclipse. For a few fleeting minutes, it fits with perfect precision. Not too large, not too small, just enough to hide the solar disk while leaving the luminous corona blazing around it. It's among the most sublime spectacles in nature. But that perfection, that impossible fit, is itself a mystery. We're told it's coincidence. The sun is about 400 times wider than the moon, yet it's also about 400 times farther away. That precise ratio means they appear nearly identical in size to our eyes, roughly half a degree across. That's why total eclipses happen. If the moon was slightly smaller, we'd see only annular eclipses, rings of fire where sunlight still burns around the edges. If it were larger or closer, the sun would vanish completely. But for now, the geometry is flawless. The alignment is so exact that the lunar disk glides over the solar face as though the cosmos itself designed a lens cap to snap perfectly into place. It feels deliberate, engineered, yet, as modern astronomy tells us, it's not. It's the accidental outcome of countless chaotic orbital interactions. No design, no intent, only mathematics. And still the numbers are unsettling. The moon's diameter is about 3,474 kilometers. The sun's is around 1.39 million kilometers. Divide one by the other and you get roughly 400. The moon's average distance from Earth is about 384,400 kilometers, while the sun sits nearly 149.6 million kilometers away. Again, divide those numbers and you get nearly 400. It's not perfect. These figures shift slightly as the orbits stretch and contract, but they're close enough to create eclipses that seem almost impossibly exact. What are the odds? Not merely of having a moon, but of having one that produces the only total eclipses of this kind in the entire solar system. Earth alone witnesses them. Other planets have moons, some much larger, some much closer, but none form this exquisite alignment. Mars has two small lumpy companions that barely cast shadows. Jupiter's grand moons never cross the sun's face so precisely. This phenomenon belongs solely to Earth, the one world known to cradle life. Some dismiss it as chance. Others sense meaning, perhaps even a hint of purpose. For centuries, people have looked at eclipses and seen omens, divine struggles, or messages from the heavens. Today, speculation persists. Is it truly random, or is there a deeper symmetry we've yet to grasp? There's another layer to it. The moon's orbit is not frozen, it's expanding. As we've already seen, it's receding from Earth by about 3.8 centimeters each year. Long ago, it was closer and appeared larger in the sky. Eclipses then lasted longer and covered the sun more completely. In millions of years to come, the moon will be too distant, too small to hide the sun's face at all. Total eclipses will end. We're living in a slender window of time, a cosmic blink, when this alignment is possible. Out of billions of years in Earth's history, past and future, we exist in the brief moment when the moon and sun appear as equals. That's not just rare, it's infinitesimal. We are standing inside a fleeting coincidence that will soon pass into memory. There are other curious symmetries. The moon rotates once on its axis every 27.3 days, exactly the same time it takes to orbit Earth. That's why we always see one face. It's gravitationally locked, always turned toward us. But its path isn't a perfect circle, it's an ellipse. Sometimes it draws nearer at perigee, and sometimes it drifts farther at apogee. That is why the moon sometimes looks a little larger or smaller in our sky, and it is the reason we experience different kinds of eclipses. Yet even those variations are not random. They unfold according to mathematical rhythms that repeat through time. One of the most remarkable of these is known as the Saros cycle. It is a pattern of eclipses lasting approximately 18 years, 11 days and 8 hours. After each of these cycles, the Earth, the Moon, and the Sun return to almost the same positions in space, and nearly identical eclipses occur again. Long before modern science could explain such alignments, the ancient astronomers of Babylon had already recognized their order. Thousands of years ago, they charted the heavens, transforming what seemed like chaos into a geometry of precision. Today, we continue to peel back the layers of that cosmic order. Science does not see meaning in coincidences. It seeks to reveal the mechanisms that create them. Orbital mechanics can describe the moon's distance, its motion, its rotation. With mathematics, we can reconstruct its journey from the moment it first formed, and we can predict how it will evolve far into the future. But mathematics does not answer the deeper question, the one that reaches beyond measurement. Why now? Why at this exact era do we live beneath a sky where the moon fits the sun with such perfection, producing total eclipses that seem made for our eyes alone? Some argue this is merely the anthropic principle at work. We notice because we are here to notice. Others suspect these alignments may whisper of laws not yet known, deeper harmonies within the cosmos itself. And there are those on the fringes who suggest something stranger still, that perhaps the moon was not born by chance, but placed its path chosen by design. These notions find no support in mainstream science, yet they persist because the numbers feel so deliberate, as if written into the very fabric of space-time. Even without crossing into speculation, the truth remains extraordinary. The moon's size and distance are tuned with such uncanny precision that together they create one of nature's greatest performances, the total solar eclipse. For thousands of years, these fleeting moments of darkness have stirred fear, curiosity, and wonder, stopping entire civilizations midday. But this alignment will not last forever. Each eclipse is part of a countdown. In the distant future, total eclipses will vanish. The moon will drift farther away, its shadow shrinking. One day, long after we are gone, no living creature on Earth will ever stand beneath a sun completely covered. They will see only partial darkness, a smaller, dimmer spectacle. So when the sky darkens and the stars emerge in the middle of the day, remember you are witnessing a cosmic coincidence, timed with breathtaking precision. The moon and the sun align, not because they must, but because somehow in this brief chapter of cosmic history they can. Whether by chance or design, the result is the same, a celestial harmony that keeps us wondering if there is more to the moon than we have yet understood. It seems impossible, almost absurd, that something orbiting our planet could be older than the planet itself. After all, the moon is thought to be Earth's child, born from the same ancient cloud of dust, or perhaps from a colossal impact that tore part of Earth away. But hidden within its crust are clues that challenge that story. Some of those clues have forced scientists to question nearly everything they once believed about when and how our nearest neighbour came to be. Certain regions of the moon appear to be not merely ancient, but older than Earth itself, pre-Earth, ancient, and that should not be possible. When the Apollo astronauts returned with lunar samples in the late 1960s and early 1970s, researchers expected to find rocks roughly the same age as Earth's, perhaps slightly younger, depending on which theory of lunar formation proved correct. Instead, they uncovered anorthosites, the bright, reflective rocks that make up the lunar highlands. These stones were unimaginably old. Radiometric dating placed some at 4.46 billion years, only a few tens of millions of years younger than the solar system itself. That figure is staggering. It tells us these rocks crystallized while the solar system was still a swirling disk of dust, gas, and colliding planetary fragments. Here is the surprise: the oldest rocks found on Earth are significantly younger. The oldest confirmed terrestrial samples date to about 4.03 billion years, over 400 million years younger. The difference does not mean Earth did not exist yet. It means that Earth's surface has been endlessly rewritten. Plate tectonics, erosion and volcanic activity recycle its crust, erasing its oldest memories. The Moon, by contrast, is geologically silent. It has no atmosphere, no erosion, no shifting continents. Once something forms there and survives an impact, it can remain preserved for billions of years, a frozen relic from the dawn of the solar system. And yet even this preservation conceals a deeper mystery. Tiny crystals known as zircons, discovered within Apollo samples and in lunar meteorites, have been dated to 4.51 billion years ago, older than Earth's first solid crust. That is before our world even took shape. Some of these crystals may have existed before the Moon itself, remnants from other ancient worlds drawn together during its violent birth. If that is the case, then these fragments are not only older than Earth's surface, they may predate Earth entirely. Such an idea reopens one of the oldest debates in planetary science, the question of how the Moon began. The leading explanation, the giant impact hypothesis, proposes that a planet roughly the size of Mars collided with the young Earth about 4.5 billion years ago, and from that cataclysm, the Moon condensed from the debris. Yet if parts of the Moon are older than Earth's crust, something does not quite fit. Could these materials have endured that unimaginable impact, or perhaps they came from the impactor itself, the lost planet called Theia? If so, what does that make the Moon? A fusion of two worlds, a surviving shard of a vanished planet, a cosmic time capsule preserving stories from places that no longer exist. Some scientists now suspect that the Moon may not have been built entirely anew from that impact. In these models, the collision did not erase everything. Instead, it gathered fragments of already formed bodies, each with its own complex past. Those rocks, those crystals, each carried a memory from before the Moon came to be. So when we say the Moon holds material older than Earth, we are speaking not only of age, but of inheritance. The Moon is built from recycled planetary history, a mosaic of worlds that collided, shattered, and coalesced over eons. There is even a more radical possibility that the Moon itself may have formed before Earth. It is not a mainstream view, but some models suggest that if Theia was a fully developed planetary embryo orbiting closer to the Sun, it might have cooled and solidified before the proto-Earth did. When the two worlds collided, the Moon could have retained parts of that earlier, more mature body. In that case, our celestial companion would truly be the elder sibling in this gravitational duet. The oldest lunar rocks where this story is written are found mostly in the Moon's highlands, the bright, cratered expanses that contrast with the darker lunar seas. These highlands are believed to be the remnants of the Moon's original crust, born when an ocean of molten rock cooled and began to crystallize. Imagine that scene. The whole Moon, a glowing sphere of lava suspended in darkness, shining like an ember against the void. As it cooled, lighter minerals floated upward, solidifying into the first crust. Those early minerals became the highlands, and some of those very rocks are still in our hands today. These ancient samples are not just old, they are unique. They contain no water-bearing minerals. They bear the marks of formation in a vacuum, under searing heat, without the shield of an atmosphere. They are relics from a time when the solar system was violent and young. Each crater, each fracture tells of impacts and upheavals from that chaotic era. While Earth's early record has been erased by plate tectonics and erosion, the Moon kept its memory intact. Even the lunar meteorites that find their way to Earth, rocks launched from the Moon by massive impacts, carry that same history. Some of them show signs of intense shock and melting evidence of collisions that happened long before the Earth-Moon system found its balance. These are not merely stones. They are survivors, fossils from a time before our planet even existed. It is a humbling thought that the Moon, which we have always regarded as Earth's child, might instead hold the oldest remnants of the solar system. Within its crust may lie the best preserved record of an age before oceans, before continents, before the stability that allowed life to begin. We have walked upon it, left our footprints and our flags, yet we are only beginning to grasp what lies beneath our feet when we stand on the Moon. Beneath that grey dust, beneath the scars of countless impacts, is a deeper story older than Earth itself. A record written in unyielding stone, unchanged by time. Parts of the moon are older than any rock we have ever touched. And the more we study them, the more they remind us that our planet is but one brief chapter in a far greater cosmic tale. The moon quietly and faithfully holds the preface. It sounds almost like fiction. That silent, pale companion drifting through our night sky has a tail, a real physical tail, just like a comet. And stranger still, that tail brushes across Earth. Not metaphorically, not symbolically, but literally. Once each month our planet passes through a faint stream of particles drifting away from the moon, like smoke rising from an unseen fire. It happens silently, invisibly, and hardly anyone on Earth knows it is happening, though it always has. The tail is not made of rock or gas, and it cannot be seen with the naked eye. It is composed mainly of sodium atoms, small and delicate particles, that are ejected from the surface of the moon and propelled outward into space. Though minuscule, they travel tens of thousands of kilometers, gathering into a vast and diffuse stream that trails behind the moon like a transparent ribbon. This is not a poetic fantasy. It is something we have measured, observed, and confirmed, and every month for a short time the Earth moves straight through it. The discovery of this sodium tail dates back to the late 1990s, when astronomers, using extraordinarily sensitive instruments, detected a faint trace of sodium light near the new moon, a light that should not have been there. Sodium, when energized, glows with a particular shade of yellow-orange. Researchers noticed that this glow waxed and waned across the lunar cycle, and when they mapped the pattern, it revealed something astonishing. A vast tail like that of a comet, extending from the moon, streaming away in the direction opposite the sun. It begins with micrometeoroids, tiny fragments of rock from space that constantly bombard the lunar surface. Because the moon lacks an atmosphere, these impacts strike with tremendous force for their size, vaporizing small amounts of rock and releasing atoms into space. Among them is sodium, a restless element that resists bonding and is easily driven outward by the pressure of sunlight. The radiation from the sun acts like an invisible breeze, nudging those atoms away from the moon until they stretch into a luminous tail that can reach beyond 100,000 kilometers. This tail always points away from the sun, just as a comet's does. And during the new moon, when the moon lies directly between the Earth and the sun, our planet moves briefly through the densest region of this invisible stream. We do not feel it, we do not see it. Yet for a few hours each month, the Earth is bathed in a whisper of lunar atoms. The tail itself is unimaginably faint, detectable only with sophisticated instruments refined over decades. Specialized devices known as sodium spectrometers can perceive its distinct glow during the new moon, appearing as a dim, hazy patch of light. Invisible to our eyes, but unmistakable through proper filters. It has no physical influence on Earth. It does not alter the weather, disturb the magnetic field, or make us glow yellow. But its existence is a quiet revelation. The moon is not lifeless. It is not still. It breathes, shedding atoms, engaging with its cosmic surroundings in ways we are only beginning to recognize. And sodium is only part of the story. Other elements escape the surface too: potassium, helium, argon. They form what scientists call the lunar exosphere, an exceedingly thin layer of gases enveloping the moon. It is nothing like Earth's atmosphere. You could not breathe it nor even detect it without instruments. Yet it exists, and it shifts and changes. Micrometeorite activity varies throughout the year, increasing during events such as the Leonid meteor shower, when Earth and Moon pass through dense trails of cometary debris. At those times the moon is struck more often, and its sodium tail brightens and lengthens. More impacts mean more vaporized atoms, a stronger exhalation from the lunar surface. Solar activity also contributes. When the sun flares or releases bursts of charged particles, the added energy can dislodge even more material. The tail is not static. It fluctuates, expands, and contracts the moon's subtle ghostly pulse in response to the forces of space. In 2006, as NASA's Messenger spacecraft journeyed toward Mercury, it turned its instruments toward the Moon and detected this tail stretching more than 600,000 kilometers, over 1.5 times the distance from the Earth to the Moon itself. Imagine that. Something trailing from our Moon, sweeping across space on a planetary scale, and yet so ethereal that it escaped our notice until recent decades. It transforms how we see the Moon. No longer a dead, unchanging rock, but a dynamic world, continually releasing material, continually interacting with the solar wind, continually whispering its presence into the dark. It is a process we cannot feel, cannot witness, but it happens above us every single month. And perhaps the most extraordinary truth of all is that we are part of it. The Earth, vast and solid, drifts through this spectral trail of lunar breath, a silent encounter between two celestial companions. The Moon has a tail, and once each month it brushes the Earth quietly, invisibly reminding us that the universe, even in its stillness, is alive with motion and connection. For countless billions of years, we've imagined that nothing changes up there. The craters remain, the dust lies still, and the landscape seems frozen in time. It feels eternal, unshaken, and utterly still. Astronomers rely on that stability, using the lunar surface to calibrate instruments and align telescopes. Yet beneath that quiet and ancient face, the Moon hides a secret restlessness, because it quakes, and some of those tremors could one day endanger the bases we plan to build there. They are known as moonquakes, and they are entirely real. When the Apollo astronauts ventured across the lunar plains, they did far more than raise flags and gather rocks. They left behind instruments, seismometers, delicate ears pressed to the Moon's interior, listening for whispers of movement from within. What they heard transformed our understanding of this world forever. Over the years, those instruments recorded thousands of quakes, and not all of them were small. A few were immense, resonating for minutes and sending energy pulsing through the Moon's body. Unlike the quakes of Earth, which arise along fault lines or within subduction zones, the Moon's quakes belong to 4 distinct kinds, each born from a different cause, and each behaving in its own peculiar way. The first are the deep moonquakes, rumbling between 700 and 200 kilometers below the surface. They seem to follow a pattern linked to the tides of gravity between Earth and the Moon. As Earth pulls on its companion, stress builds within the lunar interior until it suddenly releases in rhythmic bursts of seismic energy deep below. Then come the shallow moon, quakes rarer, closer to the surface, and far more alarming. These occur just tens of kilometers down, and some have reached magnitudes of 5.5 on the Richter scale. That may sound modest compared to our planet's greatest quakes, but on the Moon, with its brittle crust and lack of moisture, such an event would shake a structure far more violently. A tremor of that size could rattle a habitat for tens of minutes with no air, water, or soft soil to cushion the movement. For the engineers dreaming of lunar bases or permanent settlements, this is no trivial matter. Between 1969 and 1977, the Apollo seismic network detected 28 of these shallow quakes, strong enough to be sensed from great distances, some lasting over 10 minutes. That persistence is what makes them so extraordinary. Here on Earth, seismic waves fade quickly, their energy absorbed by oceans and molten rock. But the Moon is bone dry and rigid. Once set in motion, vibrations echo around inside it like sound, within a great bell continuing long after the initial strike. You do not get a single jolt, you get an extended chorus of trembling resonance. There are also thermal moonquakes, triggered by wild temperature swings. The Moon has no air to buffer the heat of the Sun, so daytime temperatures soar to about 127 degrees Celsius, and by night they plunge to minus 173. That is a shift of more than 300 degrees every lunar day. As dawn breaks and sunlight floods the surface, the rock expands, creating cracks and fractures, tiny adjustments that register as small quakes. You would not feel them in a spacesuit, but they are always there, the surface gently clicking and popping as it adjusts to the violence of its thermal cycle. It is as though the whole world creaks under the weight of its own ancient fatigue. And then there are impact moonquakes, born of collisions with meteoroids. The lack of atmosphere means space. Rocks strike the surface without burning up, slamming straight into the ground. A single large impact can send ripples of seismic energy racing through the lunar body, stirring vibrations far from the site of collision. One sufficiently powerful strike, or one that lands too near a settlement, could damage structures or destabilize the ground itself. All of this poses a profound challenge for the next generation of explorers. NASA's Artemis program, China's Chang missions, and private ventures like SpaceX and Blue Origin all plan to establish a lasting human presence on the moon. That means preparing not only to survive the journey there, but to endure the moon itself. Engineers must design habitats capable of withstanding long, resonant shaking on a surface that behaves like a tuning fork struck by cosmic forces. Buildings will need to absorb energy rather than resist it. Foundations must cling to loose, dusty terrain, and every system from power lines to scientific instruments has to be protected against sudden jolts that could snap cables, topple modules, or disrupt delicate experiments. And because shallow quakes strike without warning, it is not a question of if but when. The moon has no global monitoring system, no network of satellites watching for tectonic strain. It sleeps in silence, waiting restless beneath its ageless skin. The most we can do for now is examine the ancient Apollo records and make educated guesses about where the next tremors might strike. Future explorers will have to bring an entirely new generation of seismic instruments, exquisitely sensitive and networked, to re-establish that early warning system and perhaps even anticipate moonquakes before they happen. What complicates matters is that many of the shallow quakes logged decades ago took place near areas now targeted for permanent bases, such as the lunar South Pole, where water ice could be concealed in craters that never see sunlight. These locations are immensely appealing for exploration, but if they remain seismically restless, they may endanger any long-term human presence. Some scientists suspect these tremors are aftershocks of an ancient world still cooling down. The dying heartbeat of the moon's fiery youth, expelling the last warmth born from its creation. Others think these quakes belong to an ongoing, gradual geological process, quiet, steady, but unyielding. The moon is not lifeless. It only sleeps, and from time to time it turns in its slumber. In 2019, when researchers revisited Apollo's seismic archives, they found something extraordinary. One of the shallow moonquakes lined up almost exactly with a newly discovered fault line, a ridge formed where the lunar crust has compressed. That means the surface of the moon may still be shifting, inch by inch, cracking under its own gravity, subtly reshaping itself and releasing energy deep within. If that is true, then our future outposts will not rise upon a silent monument of stone, but upon a restless, evolving body whose inner workings remain largely unknown. Yes, the moon does quake, and some of those quakes have strength enough to shake instruments, to threaten habitats, to remind us that even the oldest, most cratered, airless worlds still move, still breathe. The next time you gaze at the moon and its tranquil face looks back, remember that beneath that serenity something ancient continues to stir quietly, slowly, and sometimes with enough force to make the stars themselves seem to tremble. One of astronomy's most enduring misconceptions is the phrase, the dark side of the moon. It echoes through songs, films, and conversation, conjuring an image of a frozen hemisphere cloaked in eternal night, hidden from all light and all understanding. People imagine it as a realm of shadow, untouched and unknowable, but the truth is far simpler. The so-called dark side is not dark at all. It receives exactly the same amount of sunlight as the face we see from Earth. What it truly is hidden. To grasp how this illusion took hold, we must first understand the moon's motion. The moon is tidally locked to our planet, which means it rotates on its axis at precisely the same pace it orbits Earth, once every 27.3 days. Because of that perfect rhythm, the same hemisphere always faces us. We see one side endlessly, while the opposite remains invisible from Earth without spacecraft to reveal it. But sunlight pays no attention to vantage points. The far side experiences day and night just as the near side does. Half the time it glows fully illuminated, the other half it rests in shadow. There is no permanent night, no cosmic darkness. The only shadow lies in our perception. So how did the phrase come to be? It was born mostly from misunderstanding. Before the era of spaceflight, the far side was unseen, beyond reach, beyond telescope, an unseen frontier. And when something cannot be seen, the human mind often paints it in darkness. The words dark side became a poetic stand-in for unknown side, but scientifically it could not be more inaccurate. The illusion was finally dispelled in 1959 when the Soviet probe Luna 3 captured the first blurred photographs of the far side. What those images revealed astonished scientists everywhere. The unseen hemisphere looked completely different, densely cratered, rugged, with almost none of the smooth shadowed plains we recognize as Luna Maria. Those dark patches on the near side are ancient basaltic fields, frozen remnants of lava that once flowed billions of years ago. The far side has almost none of them, just a few small plains scattered among highlands, scarred by impact after impact. It is a world shaped by violence, untouched by volcanic renewal, and now at last seen in the light. Why is there a difference? It remains one of the great puzzles scientists are still striving to unravel. One explanation proposes that the crust on the far side of the moon is thicker, making it more difficult for molten rock to rise and spread across its surface. Another idea points to the early Earth, which may have influenced how heat was distributed through the moon, when both worlds were still glowing oceans of magma, in effect baking one hemisphere more than the other. The outcome is a celestial body with two faces, shaped by ancient cosmic forces that we are only beginning to comprehend. But there is a twist to this story. The far side is no longer a complete mystery. Using instruments of astonishing precision, we have mapped it in extraordinary detail. The Lunar Reconnaissance Orbiter, the Chang missions, and other spacecraft have captured high-resolution images of every crater, ridge, and plain. The so-called dark side is now among the most intensely studied landscapes in the entire solar system. We now know its contours even better than we know parts of Earth's ocean floor. The far side has become so well charted and so distinctive that it is now a prime target for future exploration. In the year 2019, the Chang'e 4 mission achieved something no one had ever done before, landing both a spacecraft and a rover within the von Karman crater on the far side of the moon. Because this hidden hemisphere faces away from Earth, direct radio communication is impossible. Yet China overcame that challenge by deploying a relay satellite named Queqiao into lunar orbit, creating a link that allowed the lander to speak to controllers across the void. That moment marked more than a technical triumph. It redefined how we think of the far side itself. It is not dark nor unreachable, merely concealed, and even that is changing. Still, the mythology of the dark side lingers, perhaps because it touches something deeply human, a fascination with the unseen. We are drawn to places beyond our view, convinced they hold secrets, dangers, truths that daylight cannot expose. For countless generations, the moon's hidden face was the ultimate unseen world, turning silently above us forever, keeping its mysteries. It became the perfect canvas for imagination. We filled that unseen hemisphere with fantasies of aliens, secret bases, conspiracies, all safely tucked beyond sight. But science has stripped away the illusion, and in doing so revealed something far richer. The far side of the moon is real, ancient, and profoundly alien. Its surface bears scars that date back to the birth of the solar system, preserving craters so old and so untouched that they might reveal what the moon looked like before Earth even had oceans. Someday that silent landscape could host radio telescopes protected from the interference of Earth, or research stations buried beneath the lunar dust. It might even become the first home for humans on the moon, beyond the reach of radio waves, in the place we once called the dark side. So perhaps it is time to let go of the myth. The far side of the moon is not dark, not malevolent, not hiding by choice. It is simply the result of gravity and orbital mechanics, a cosmic dance that keeps one face turned toward Earth and the other forever gazing into deep space. And thanks to modern science, we are no longer blind to that hidden world. We have seen it, mapped it, landed upon it, and in doing so transformed it from mystery into frontier. Rust, we once believed, was a phenomenon unique to Earth. It forms when iron meets both water and oxygen, a chemical reaction that turns metal red and brittle. We see it on forgotten bridges, derelict cars, corroded tools. It seemed impossible that rust could exist on the moon, a place with no atmosphere, no liquid water, no air. dry, lifeless, and exposed to the vacuum of space. And yet somehow scientists have found rust there. Real, unmistakable rust. The discovery came in the year 2020. Researchers studying data from India's Chandrayaan-1 orbiter noticed something unusual. The spacecraft carried an American-built instrument called the Moon Mineralogy Mapper, designed to analyze the composition of the lunar surface. Most of what it detected was familiar silicates, pyroxenes, olivines, and minerals rich in iron. But then the data revealed something extraordinary: spectral fingerprints resembling hematite. Hematite is a form of iron oxide, a true rust, meaning the metal has reacted with both oxygen and moisture. That raised a startling question. How could hematite form on the moon when the necessary ingredients are absent? No liquid water, no breathable air, only the harsh solar wind and desiccated rock. At first, scientists suspected a mistake, a data glitch, a misinterpretation. But when they checked again, examining other lunar regions, different angles, varying light conditions, the signature persisted. The presence of hematite kept appearing predominantly across the higher latitudes of the moon near its poles, and curiously, on the far side. Not everywhere, but often enough to command attention. This was no random occurrence. Something was quietly corroding iron on the moon. And that left scientists with a question that seems almost impossible to answer: how one theory points to an unexpected suspect, the Earth's own atmosphere. It appears that our planet's magnetic field stretches far into space, much farther than we might imagine. As the moon completes its orbit, it sometimes drifts through a region known as the magnetotail, a long extension of the Earth's magnetic influence. During those times, the moon is momentarily protected from the solar wind, and within that brief protection, it moves through a faint stream of oxygen atoms leaking from Earth's upper atmosphere. It is a tenuous thread of our air, stretching millions of kilometers into the void, and once every lunar month, the moon glides through it like a passing brushstroke. In that fleeting moment, there is oxygen, not much, but perhaps just enough. If iron-bearing minerals on the lunar surface are exposed to this oxygen, especially in places where frost or trace water molecules lie hidden within the regolith, then, under the right conditions, oxidation might proceed ever so slowly, unfolding over millions of years on a world where nothing should rust. Adding another layer to the mystery, we now know that water molecules do exist on the moon. Not as pools or glaciers or even shards of ice, but as faint molecular traces trapped in the grains of lunar soil. Some of this water likely forms when protons from the solar wind strike the surface and interact with oxygen atoms in the regolith, creating hydroxyl compounds. And deep in permanently shadowed craters near the poles, even solid water ice has been detected. So perhaps, just perhaps, there is enough of this subtle moisture combined with those periodic whispers of Earth's oxygen to allow rust to emerge in one of the most improbable environments imaginable. And here lies a curious twist. The rust appears more abundant on the far side of the moon, the hemisphere that never faces Earth. That feels backward, doesn't it? You would expect the near side to receive more of Earth's oxygen. But the explanation may rest in the way solar wind particles strike the moon. The near side, facing the sun, more directly endures constant bombardment from charged solar particles. Those energetic protons might actually prevent oxidation by knocking oxygen atoms away. The far side, more sheltered during certain parts of its orbit, may offer a haven where these delicate reactions are allowed to persist. This discovery reshapes our understanding of the moon. It suggests that its surface is far more chemically active than once believed, not a static layer of dust, but a place where gentle, invisible processes continue to unfold, even now. It also reveals an unseen bond between Earth and its companion, one that extends beyond gravity alone. Our atmosphere reaches across space, shaping the very chemistry of the lunar soil. The moon, it seems, is not as separate from Earth as we once thought. And perhaps the most remarkable insight of all is this: rust does not simply tell the story of the moon's past, it may illuminate its future. By studying where hematite forms, scientists could identify hidden reservoirs of water within the lunar regolith, knowledge that could be vital for the next generation of explorers. If we are To live on the moon, we must know where to find water, not only for drinking, but to create oxygen and even rocket fuel. Rust might become the quiet clue that guides us to those essential resources. There is a poetic symmetry in that. Rust, the symbol of decay on Earth, the emblem of time's relentless wear, might instead show us the way forward to survive, to build, to endure on another world. So yes, there are places on the moon where rust has taken hold. Rust in the absence of air. Rust where no rain has ever fallen. One of the gentlest chemical wonders of the solar system, playing out in silence across the dust. Proof that even in desolation, chemistry still dances. The moon keeps its secrets, and sometimes they shimmer red. We tend to picture the moon as a dead, unchanging sphere, cold, still, and timeless, its surface scarred by impacts across billions of years. But perhaps beneath that ancient crust, there lies something far more intricate. Perhaps it is not merely craters and plains, but a world that once flowed with molten fire, a hollow network of tunnels carved not by alien hands but by rivers of lava, because evidence is growing that the moon may once have harbored vast lava tubes stretching for miles beneath its surface, and that some of them may yet remain intact. Let us turn back the clock 3 to 4 billion years. In its distant past, the moon was anything but still. It was a world alive with geological energy at its surface, reshaped by waves of molten rock pouring from erupting volcanoes. These glowing rivers spread across the landscape, smoothing craters and leaving behind the dark, sprawling regions we now call Maria, the lunar seas. They are vast plains of basalt born from eruptions, so immense they coated the moon's face like syrup spreading across a dish. But what most people never imagine is that lava rarely flows only across the open ground. On Earth, it can move beneath the surface too, carving long, hollow tunnels known as lava tubes. They form when the upper layer of a lava stream cools and solidifies, while the molten core within continues to move downward, insulated by its hardened shell. When the eruption finally ends, and the molten rock drains away, what remains is an empty corridor, a natural conduit sculpted by fire. We see them in places like Hawaii, Iceland, and the Canary Islands. Some are narrow enough to crawl through, while others could easily fit a vehicle. Evidence now suggests that the same process may have shaped the moon on a far grander scale. Lunar orbiters have revealed strange circular openings, skylights dotting the surface of ancient lava plains. These are not the scars of impacts. They are too smooth, too sharply defined, often leading straight down into darkness. NASA's Lunar Reconnaissance Orbiter has imaged several of them in regions such as Marius Hills and the Sea of Tranquility, where they appear to open into collapsed chambers beneath the ground. These are almost certainly entrances to lunar lava tubes. Some skylights measure tens of meters across, while the tunnels below could span hundreds of meters in diameter and stretch for miles. Analyses of lunar gravity and collapse patterns suggest that these tubes might reach extraordinary widths, perhaps 1,000 meters, more than half a mile across, making them far larger than any known on Earth. The moon's weaker gravity allows rock to arch more easily, keeping such enormous structures stable, and that makes them not only scientifically intriguing but potentially useful, because the moon's surface is an unforgiving place. It endures constant radiation from the sun, is struck by micrometeorites, and experiences temperature swings from 127 to 260 degrees in the sunlight down to negative 173 to negative 280 degrees in darkness. To live on the surface would mean endless shielding and reinforcement, but inside a lava tube, the thick rock overhead would act as a natural fortress. It would block radiation buffer against impacts and smooth out the violent thermal extremes. You would not need to build bunkers, the moon has already built them for you. This idea has drawn serious attention. Japanese scientists, using their Selene orbiter, discovered what may be a giant lava tube under the Marius Hills. NASA and the European Space Agency have run simulations exploring what living in such a place might be like. Architects have imagined vast underground bases nestled within these ancient tunnels, pressurized corridors with living quarters, laboratories and farms, bathed in artificial light, safe beneath the lunar crust. But the value of these tubes is not limited to shelter. Because they have been sealed for billions of years, they may preserve an untouched archive of the moon's history. While the surface has been blasted and baked by radiation and impacts, the interiors of these tubes could still hold pristine rock-trapped gases or even ice-frozen remnants of the moon's fiery youth. They could tell us how the moon cooled, how it evolved, and what secrets still lie hidden in its depths. Some researchers even suspect these tunnels might connect into immense networks, an underground labyrinth stretching beneath the lunar seas. On Earth, lava tubes often branch and merge, forming complex cave systems. If that is also true on the moon, then beneath the quiet grey surface could lie a vast unseen world carved by ancient fire. For now, we have only glimpsed the edges of this mystery. No human or robot has yet entered a lunar lava tube. We do not know how far they reach, how strong their ceilings are, or what truly waits inside. But future missions may change that. Rovers could one day descend through skylights, mapping voids and exploring the darkness, and perhaps someday a person will follow. Imagine the moment when a human steps into a natural tunnel, untouched by sunlight for 3 billion years, a silent cathedral of stone, older than any monument on Earth, shaped by forces beyond imagination. A realm of quiet where time itself seems to hold its breath. Here the moon guards the oldest memories of the solar system. These tunnels carved within its crust are not mere voids in rock. They are the frozen veins of a once fiery world, remnants of an age when molten rivers flowed beneath its surface, and perhaps in their silence they hold the blueprint for our next steps among the stars. It may sound fantastical, yet the moon could possess a vast labyrinth of lava tubes, literal caverns, stretching for miles, formed when its volcanic heart still pulsed with energy. This is not a tale of science fiction. It is a story written in the language of science, one that waits for us to uncover it. For all its stillness and desolate calm, the moon is not as lifeless as it might appear. During the Apollo era, astronauts witnessed something unexpected moments that challenged the idea of the moon as a dead, inert sphere. They saw bursts of light, fleeting, spontaneous flashes dancing across its surface. Some glowed softly for a second or two, others pulsed like tiny sparks. These were not illusions born of fatigue or tricks of the eye. Such events had been observed centuries before the first spacecraft left Earth, and even today telescopes continue to record them. Scientists call them transient lunar phenomena. Take the story of Apollo 11. While orbiting the moon, astronaut Michael Collins noticed a sudden shimmer of light, something that simply should not have been there, and he was not alone. Across other missions, similar reports emerged, flashes, faint illuminations that would flicker into existence and vanish just as quickly. They were not reflections from the spacecraft, nor signals from instruments. They appeared to come from the moon itself. Yet this mystery stretches far beyond the space age. It reaches back to the late 18th century, when the astronomer William Herschel, the man who discovered Uranus, claimed to have seen glowing lights on the lunar surface. He thought they were volcanoes. Since then, hundreds of sightings have been logged by professionals with observatories and by amateurs gazing from their backyards. Many of these lights appear near the Aristarchus crater, a region that has long carried whispers of strange activity. These phenomena vary dramatically. Some are quick flashes, like stars flicker into life for an instant. Others are hazy patches or shifting clouds of brightness that linger for seconds or even minutes. Occasionally they bring a wash of colour, soft pinks or blues rippling briefly across the grey landscape. They emerge without rhythm or reason, frustrating those who try to study them. For centuries, skeptics dismissed them as illusions caused by Earth's turbulent atmosphere, the shimmering distortion that bends light and deceives the eye. But then came the Apollo data, and the debate changed. If astronauts floating in the vacuum of space were witnessing these same flashes, then atmospheric distortion could no longer be the culprit. Something real was happening on the moon. So what could it be? The theories are many, and none have yet claimed victory. One idea suggests that micrometeoroids constantly pepper the lunar surface. When they strike, they release bursts of heat and energy, vaporizing grains of dust and perhaps freeing gases, argon, helium, even radon from deep within the crust. If these gases escape, they could briefly glow in the sunlight, forming luminous puffs or flashes of light. Apollo instruments detected faint traces of such outgassing, hinting that while the moon is not geologically alive like Earth, it still breathes in subtle, ancient ways. Another possibility involves electricity. The moon's surface is covered in a fine, powdery dust called regolith, which becomes electrically charged by solar radiation. When darkness falls, or sunlight suddenly returns to a shadowed region, that charge can shift. The dust may rise or discharge, creating tiny sparks of light, static electricity on a cosmic scale. These flickers could be the source of some of the mysterious flashes. And then, of course, there are meteoroid impacts. NASA telescopes have captured them, bright pinpricks lighting up the lunar surface during meteor showers. Each collision releases a quick, brilliant pulse of light. Most are too faint to see without special equipment, but some are visible even to the naked eye, especially against the stark blackness of space. Still, none of these explanations account for every sighting, especially those strange glowing patches or sudden changes in colour that linger longer than a simple flash. That is what keeps the mystery alive. Transient lunar phenomena defy tidy categorization. They are rare, unpredictable, and fleeting. The moon, as always, keeps its secrets close. Even in this era of satellites orbiting Earth and robotic explorers traversing the lunar surface, the mystery of those fleeting lunar lights endures. Modern science has rekindled its fascination with these strange occurrences. In the year 2019, a group of German scientists set up a robotic telescope in Spain designed to watch the moon every night, patiently waiting to catch these transient lunar phenomena in action. Their efforts have yielded dozens of intriguing observations, brief bursts of light, momentary glows, and isolated flares near well-known craters. Each image is now being scrutinized frame by frame. Many of these luminous flashes are likely caused by meteoroids striking the surface, but others continue to defy explanation. Location also seems to play a role. Certain craters, particularly Aristarchus, Plato, and Kepler, appear unusually active, attracting far more reports of these luminous events than most other regions. Is that mere coincidence? Are we deceived by optical effects? Or might these areas represent weak points in the moon's crust, places where trapped gases, internal stress, or residual heat occasionally break through the surface? Future missions could provide answers. If we place robotic landers or even human habitats near these regions, we might finally observe one of these outbursts from the ground, perhaps even as it unfolds. Sensitive seismic and electromagnetic sensors could one day uncover the hidden processes stirring beneath the surface. For now, though, we remain uncertain. What we do know is this: the moon is not merely a mirror reflecting sunlight. It sometimes releases its own light, not in a steady glow, but in sudden enigmatic flashes. The kind that make you blink and wonder if your eyes deceived you. The kind that make astronauts glance toward one another and ask, "Did you see that too?" Yes, they did. And so have we. The moon shimmers. At times it flickers. In those moments, brilliant yet brief, it reminds us how little we truly know it. Even a world we have visited, charted, and walked upon still guards its secrets etched not only in rock but in light itself. It floats silently in the void, a pale disk of stone 384,400 kilometers away. It makes no sound. It moves slowly. And yet across millennia, humanity has felt its influence, believing the moon shapes not only the tides or the turning of calendars, but also life itself, our minds, our emotions, even our bodies. The more science investigates, the harder it becomes to dismiss entirely. Because while the moon does not cast spells or whisper to us in the night, growing evidence suggests it does, in subtle ways, affect the rhythms of living beings, and yes, even us. Its gravitational pull moves the oceans. Twice each day, the seas swell and retreat in response to that invisible tug, a force so vast it reshapes entire coastlines. That part is no mystery, it is physics. Yet tides reach beyond the shore, influencing ecosystems. Countless species have evolved lives synchronized to the lunar rhythm. The grunion, a small silvery fish found along the Pacific coast, spawns according to the full and new moons. During high tide, countless fish surge onto the beaches, laying and fertilizing their eggs in the sand. 2 weeks later, when the tides again rise, their young hatch and drift back into the sea, a perfect pattern, guided solely by moonlight and gravity. In the coral reefs of the Great Barrier Reef, stationary colonies somehow sense the arrival of the full moon. Once a year, in a synchronized spectacle that spans thousands of kilometers, they release clouds of reproductive cells into the water, an event so precisely timed that it can be predicted to the hour. No clocks, no cues from weather, only the moon. Even creatures on land respond. Lions hunt more effectively during the darker lunar phases when their prey struggles to see. Wolves howl more often around the full moon, not from mythic longing, but likely due to increased nocturnal activity. Migrating birds navigate by lunar light. Nocturnal insects adjust their feeding patterns with the changing brightness of the sky. These are not legends. They are the evolutionary signatures of life, attuned to a celestial clock that has ticked above us for billions of years. And what about us, the humans, who claim to have moved beyond such influences? We no longer fish by moonlight or hunt by its glow, and yet the full moon continues to hold a strange power over the human imagination. Throughout history, it has been woven into tales of madness, transformation, crime, and birth. The very word lunatic stems from luna, the Latin name for the moon. For centuries, physicians believed that its phases could trigger seizures, mental disturbances, or violent outbursts. Myths of werewolves, witches, and rituals all orbit the same cycle. Surely science would have dispelled such notions by now, and to some degree it has. Large-scale analyses have examined emergency room visits, psychiatric admissions, crime reports, and birth rates, searching for patterns that align with lunar phases. The conclusions are uncertain at best. Most data show little measurable effect, and yet a faint signal persists, subtle, irregular, but persistent enough to intrigue researchers. In 2013, a study published in the journal Current Biology revealed that volunteers in a controlled sleep environment took longer to fall asleep and experienced less deep sleep during the full moon, even when they could not see it and were unaware of its phase. Their melatonin levels dropped, and brain scans showed disrupted circadian rhythms. This was not psychological, it was physiological. Other studies have noted small increases in seizures, anxiety, and mood changes during the full moon in certain individuals. The differences are not dramatic, but they are real enough to make us pause, to remind us that even now in our age of light and reason, the moon continues to touch life in quiet, unseen ways. Some scientists think that the moon's pull on sleep might also ripple through our emotions, thoughts, and actions. Even a gentle disturbance in our rest can unfold into subtle shifts in how we feel. For those already sensitive to mental health fluctuations, that small push could make a difference. And then there is light. A full moon can shine so brightly that it suppresses melatonin, the hormone that guides our sleep cycle. Long before cities and electricity, our ancestors would have lived beneath nights dramatically brighter when the full moon rose. That glow may have drawn them to stay awake longer, to hunt, to gather, to share stories beneath its silver wash. In that sense, the moon might have quietly sculpted not only our biology, but our habits, even our myths. Ask any nurse or obstetrician about full moons and births, and many will insist the two are linked. The data, though, tell a mixed story. Some studies show a faint rise in spontaneous labour during full moons, while others reveal none at all. Yet the belief endures not because it is proven, but because it feels witnessed, an echo of patterns noticed across time. Perhaps the moon does not cause labour, but coincides with slight environmental changes in light and gravity that influence the rhythms of our bodies. Even animals surrounded by city lights, cut off from nature, seem to react to the lunar cycle. Studies of rodents, household pets, and creatures in zoos have revealed fluctuations in activity, aggression, and sleep that track roughly with the moon's phases. The reasons remain elusive. We only know it happens. No, the moon does not transform people into monsters or drive them to madness. It moves more delicately, almost imperceptibly, like a hand adjusting the mechanism of a hidden clock. It stirs fluids, hormones, and instincts through gravity, through light, and through forces we have yet to name. The moon is neither ruler nor bystander. It is a cosmic companion that shapes tides, migrations, sleep cycles, and perhaps the emotions we carry within us, not through command but through rhythm, a rhythm life has followed for billions of years. Even if we no longer hear it, the melody still hums softly through every living thing, including us. For decades, humanity saw the moon as a barren desert, scorched by sunlight, stripped of atmosphere, and utterly devoid of something as fragile as water. That conviction held even after the Apollo missions brought lunar rocks home. Those samples looked dry, and early instruments found no trace of water. The moon was dust, stone, and silence. That was the story. But the story was incomplete. Because there is water on the moon in more places and in stranger forms than anyone imagined, the deeper we look, the more surprising the truth becomes. Here is the twist. The Apollo samples did contain water. We simply lack the tools to find it. The instruments of the 1970s were not sensitive enough to detect water trapped deep within the crystalline structure of the rocks. When scientists revisited those samples with newer methods, they found microscopic glass beads born of volcanic fire, each holding molecular water. The moon was not merely struck by water-rich asteroids. It once had volcanic eruptions that released magma already containing water. That means the moon's interior held traces of it long ago. But the revelations did not stop there. In the year 2009, NASA intentionally sent the L-Cross impactor crashing into a crater near the South Pole, a place locked in eternal shadow. These craters never see sunlight. Temperatures inside plunge to 250 kelvins, cold enough to freeze not only water but other volatile compounds. When L-Cross struck, it threw up a cloud of debris. Inside that cloud were unmistakable signs of water ice. That discovery shattered the idea of a dry moon. Those polar shadows conceal reservoirs of ice, not lakes, not rivers, but grains and layers mixed into lunar soil. Some estimates suggest hundreds of millions of tons of water ice may lie frozen there. And that is not all. In 2018, data from NASA's Moon Mineralogy Mapper revealed water spread across the lunar surface, even on the side bathed in sunlight. It raised a profound question. How could water survive in direct sunlight on an airless world where temperatures exceed 120 degrees Celsius? The answer lies in chemistry. The water is not liquid, nor even traditional ice. It exists mostly as hydroxyl molecules chemically bound to minerals within the dust. It is not pooled or frosted, but trapped at the molecular level, clinging to grains of silicate. Some of it might also exist as nanoscopic beads of ice, hidden inside the soil, protected from the sun's heat. This water is dynamic. Over a lunar day, it shifts. When the surface warms, some molecules escape or migrate. When night returns, they condense again, becoming part of a faint, slow cycle, a whisper of a water system that moves with light and darkness. Another clue came from India's Chandrayaan-1 mission. Its instruments found hydroxyl-rich regions clustered near the higher latitudes, far from the equator. These areas still receive sunlight, but less intensely, forming a delicate balance where water can endure without vanishing. So, where did all this water truly come from? There are three leading possibilities. The first involves the relentless impacts of comets and asteroids. These icy wanderers have collided with the moon for billions of years, scattering fragments of frozen water across its surface. Some of that water may have found refuge in deep cold craters locked away before it could escape into the vacuum of space. The second source is far stranger, born not from rock or ice, but from the solar wind itself. The moon's surface is constantly bombarded by streams of hydrogen ions from the sun, particles traveling at immense speeds. When they strike the lunar soil, they can combine with oxygen atoms in the rock to create hydroxyl or even water molecules. It is a form of chemistry powered purely by sunlight, a dance of particles shaping matter on a world without air. The third possibility is volcanic. Some of the moon's water may have been there from the beginning, trapped inside during its formation, and later released through ancient volcanic eruptions. The discovery of water molecules sealed in volcanic glass supports this idea, hinting that the moon's interior was not always as dry as we once believed. What is extraordinary is that this hidden water, in every form, could now define the next chapter of lunar exploration. NASA's Artemis program has chosen the South Pole as a key target for future human landings, precisely because of this water ice locked within the perpetual shadows. That ice could one day be collected, melted, purified, or even split into hydrogen and oxygen to make rocket fuel. Water, in this sense, becomes more than sustenance. It is the foundation for life and for exploration beyond Earth. Yet retrieving it will be immensely challenging. The ice is mixed with dust, buried beneath layers of regolith, and frozen into rugged terrain untouched by sunlight. Extracting it will demand technology, never before used on another world: drills, robotic explorers, thermal systems, and protective shelters. The water bound within sunlit soil may be even harder to reach. To free it, we would have to heat the ground, molecule by molecule, teasing it out into vapor. Still, the simple fact that it exists is astonishing. For a world once considered utterly barren, the moon reveals itself as a dynamic, evolving realm of hidden water, a world where that water clings to shadows, hides in minerals, or drifts faintly through a fragile exosphere. It is not Earth, it is not Mars, it is its own strange alien system, with just enough water to keep scientists questioning and explorers dreaming. So yes, the moon does have water, but not in the way we once imagined. It is trapped, frozen, chemically bound and in constant motion, a ghostly echo of a water cycle playing out across a world long thought to be dead. And now that we know it is there, we will never see that silent grey sphere the same way again. The moon may appear smooth and perfectly balanced from a far orbiting Earth in steady grace, but that illusion vanishes upon closer approach. Its gravity is not uniform. It wavers, bulges and dips, stronger in some regions, weaker in others. These gravitational irregularities are not minor quirks. They are so powerful that they once caused spacecraft to crash. Even today, they remain among the moon's most mysterious riddles. Gravity there is not the gentle, even pull we know on Earth. If you were to fly across the moon's surface with an instrument sensitive enough to measure every subtle variation, you would find your weight shifting constantly, heavier here, lighter, just a few kilometers away. The reason lies beneath the surface, in what scientists call mass concentrations, or maskens. These are regions where the crust contains more mass than expected, often buried deep underground. They exert a slightly stronger gravitational pull enough to tug on orbiting spacecraft and alter their paths. The effect is small but cumulative, and without accounting for it, a probe could slowly spiral off course or collide with the surface, as happened in the early years of lunar exploration. Maskens were first identified in the 1960s when NASA's lunar orbiter missions, precursors to the Apollo landings, began drifting from their predicted paths. Their carefully calculated orbits would suddenly shift as if something unseen were pulling at them. Eventually, scientists traced the cause to these hidden concentrations of mass below the surface. What is even more curious is where they appear beneath the vast dark plains known as Maria, those immense circular basins we see from Earth. Imbrium, Serenitatis, Crisium, and Humorum. These giant impact craters created billions of years ago were later flooded by lava, but beneath them something denser than solidified basalt seems to lurk. One possibility is that when the impacts occurred, the moon's crust fractured, allowing molten material from the mantle to rise and cool into these heavy regions. Another theory suggests that fragments of asteroid cores, ultra-dense metallic remnants, remain trapped below. Or perhaps the impacts themselves compressed the mantle, leaving behind gravitational scars that never healed. The truth, however, remains elusive. In 2011, NASA launched the Grail mission, two spacecraft named Ebb and Flow, to map the moon's gravitational field with unprecedented precision. What they discovered was astonishing. Maskens are far more common than we imagined, and the moon's gravitational landscape is not a simple gradient, but a chaotic tapestry of peaks and valleys, as though the crust had been twisted and folded from within. These maps revealed a hidden world beneath the surface, ancient lava tubes, buried fault lines, and traces of a once molten core. The data revealed that the moon is not merely a barren stone adrift in the void, but a dynamic, geologically intricate world sculpted by forces we are only beginning to understand. The Grail mission uncovered regions where certain mass concentrations, or mascons, are twice as dense as their surroundings, forming tight, bullet-shaped structures deep beneath the crust. This uneven distribution of gravity is more than a curiosity. It has real, tangible implications. Any future lunar base, rover, or satellite must contend with a gravitational field that defies simple intuition. A spacecraft in low lunar orbit cannot maintain a flawless circular path. It drifts, pulled subtly off course depending on the terrain below. Today, engineers incorporate these gravitational variations into their orbital models, but the earliest missions did not have that advantage. The Soviet Luna 15, competing with Apollo 11 in 1969, met its end on the lunar surface, undone, in part, by unaccounted gravitational distortions. Even now, Grail's precise gravity maps are refining the landing zones of upcoming missions. Without knowing what invisible hand is tugging at your lander, you cannot know how quickly you are falling. And on a world where the difference between a gentle landing and complete annihilation can be measured in seconds, understanding gravity is everything. But beneath this practical concern lies a deeper question. Why is the moon's gravity so uneven while Earth's is not? Our planet has volcanoes, mountain ranges, and shifting tectonic plates, far more dramatic geology, yet its gravitational field remains astonishingly smooth. The moon, by contrast, appears frozen, and still yet beneath its surface lies a strange mosaic of invisible irregularities. One explanation may lie in time itself. The moon has no atmosphere, no erosion, no tectonic renewal. Its wounds never heal. Every collision, every pulse of magma, every buried mass remains locked in place, stacked through eons like the pages of a cosmic archive. Earth's surface, ever reshaped by wind, rain, and the movement of continents, slowly smooths away its gravitational imbalances. The moon, meanwhile, preserves them as a fossilized imprint of its own turbulent youth. And here lies the poetic symmetry of it all. The same gravitational oddities that once puzzled scientists and shattered spacecraft may one day guide us toward discovery. Mascons could mark the locations of ancient heat flows, mineral deposits, or even trapped volatiles beneath the crust. Just as Earth's gravity maps reveal oil, gas, and underground water, detailed surveys of the moon's gravity might lead explorers to vital resources hidden below. So when you lift your eyes to the moon and see that calm, silvery face gazing back, remember it is not perfect nor still. It is a world of unseen distortions, where gravity bends and twists in mysterious ways, shaped by ancient cataclysms, frozen in time, still pulling on anything that ventures too near. The moon's uneven gravity is not merely an oddity. It is a whisper from its hidden core, a message carried across time, inviting us to uncover the secrets still buried in its depths. One of the most overlooked yet remarkable truths about the moon is also the most familiar. We always see the same side. Night after night, for every human who has ever lived, the same face of the moon turns toward us, the sea of tranquility, the ocean of storms, the vague shape we call the man in the moon. It does not spin before our eyes like a globe. Its far side forever hides from view. Half of it belongs to us, half remains unseen. And this is no illusion of perspective, no trick of geometry. It is a real and inevitable consequence of physics. The phenomenon is called tidal locking, and while the name sounds gentle, it is born of a fierce and ancient struggle, the gravitational tug-of-war that has lasted for billions of years. To understand it, you must think of gravity not as a static pull, but as a sculptor reshaping worlds slowly and inexorably through time. In its infancy, the moon spun much faster each day, out of sync with its orbit around Earth. If you could have stood beneath that young sky, which you could not, for Earth was then a molten inferno, you would have seen the lunar landscape change over time. But as the moon circled Earth, our planet's gravity pulled on the slight bulge caused by the moon's imperfect shape. Imagine something more like a potato than a perfect sphere. That gravitational tug acted as a brake, draining the moon's rotational energy bit by bit. Over millions of years, this process slowed the moon's spin until it synchronized perfectly with its orbit. When that balance was achieved, the system settled. The moon became tidally locked. From then on, one hemisphere faced Earth eternally, while the far side remained forever turned away. This cosmic choreography is not unique to our moon. Many of Jupiter's and Saturn's moons are also tidally locked. Even certain exoplanets may show the same phenomenon, one side scorched in perpetual daylight, the other cast into endless night. It is the universe's way of seeking equilibrium, of converting motion into stillness. Yet our moon is unique in one profound sense. Most tidally locked worlds have no witnesses. We are the rare observers on the other side, gazing up at this steadfast companion that shows us only one face. That singular fact has shaped human imagination for millennia. Our myths, our art, our science, all rooted in the same familiar surface. Before spacecraft revealed the far side, we truly had no idea what the rest of our nearest neighbor looked like. It was not until the year 1959, when the Soviet spacecraft Luna 3 captured the first grainy glimpses of the moon's far side, that humanity finally saw what had always been hidden from view. And it was astonishingly different. A world covered with countless craters, almost devoid of the smooth seas we call Maria, a landscape entirely alien. The same moon, yes, but wearing a different face, with a character of its own. It was as if a quiet companion suddenly revealed a secret life you never imagined existed. Why does the moon never turn to show us the rest? Why does the lock between Earth and moon remain unbroken? In truth, it does wobble a little, an effect known as libration, because its orbit around Earth is not a perfect circle, but slightly stretched into an ellipse. And due to the tilt of its axis, we can see about 59% of its surface over time, not merely half. It is as though the moon gently nods and rocks, teasing us with glimpses along the edges. But its core face never leaves us, for its rotation is perfectly synchronized with its orbit. This is no coincidence. It is the inevitable result of gravity's slow and patient work across vast stretches of time. Earth itself is subject to the same effect. In reverse for the moon's pull is gradually slowing our planet's spin. In the far future, billions of years from now, Earth too may become tidally locked to the moon. One hemisphere will forever face its companion, while the other will never see it again. Imagine that. Yet there is something profoundly poetic about this arrangement. Because the moon has always shown us only one face, the history of humankind has unfolded under a single vision of it. Our myths, our songs, our art, even our first steps upon its surface, all were shaped by that one familiar visage. We observed, measured, and dreamed through a narrow window, never realizing how incomplete our view truly was. The hidden half remained a mystery, and even today, with satellites and landers exploring its far side, that asymmetry still colors the way we relate to our nearest neighbor in space. And it raises haunting questions. What if the moon were not tidally locked? What if every night revealed a new face? Would we have built the same stories, felt the same fascination? Probably not. That steady gaze, unchanging through millennia, gave the moon a kind of personality, a constant presence watching over us. Whether you see a man, a rabbit, or something else entirely, that face has not altered since the first eyes looked up in wonder. The reason lies in the delicate balance of motion and gravity, a cosmic choreography, billions of years in the making. If the moon were to vanish tomorrow, not explode, not crash into Earth, simply fade away, the consequences would be catastrophic. The tides would disappear, the nights would darken, but those would not be the worst of it. The real disaster would come from something subtle, the tilt of Earth's axis. Right now, our planet leans at about 23.5 degrees. That tilt gives us the seasons. As Earth travels around the sun, one hemisphere turns toward the light while the other turns away, creating spring, summer, autumn, and winter. Without that tilt, there would be no variation, just permanent zones of heat and cold depending on latitude. But the tilt is not fixed. Over thousands of years, it wobbles like a spinning top, a motion called axial precession. Left unchecked, it could swing wildly between 0 and 85 degrees. Such extremes would devastate life on Earth, turning deserts into frozen plains, dragging the poles into the tropics, and plunging climate systems into chaos. Yet that does not happen because the moon is there. The moon acts as a stabilizer, a vast gyroscope in the sky, exerting a steady gravitational pull that keeps Earth's tilt nearly constant. Instead of veering erratically, our axis shifts only about 1.3 degrees over 41,000 years. That gentle variation governs the rhythm of ice ages and interglacial warmth, allowing life to adapt and endure rather than perish. In a very real sense, the moon has been the guardian of Earth's climate for billions of years, keeping our world calm enough for life to flourish. When scientists model a moonless Earth, the results are terrifying. The tilt could swing anywhere from 10 to 85 degrees, making the planet topple almost onto its side. Imagine the North Pole aimed straight at the sun for months at a time, blazing under continuous daylight while the equator freezes in darkness. Oceans would boil and glaciers would expand in a cycle of chaos. Ecosystems would collapse and mass extinctions would sweep across the globe. The moon's mass, perfectly proportioned, prevents that nightmare. In the end, our tranquil world, our seasons, our very stability, all depend on that silent companion in the sky. A coincidence of motion and gravity that feels almost like intention, yet is nothing more than the quiet artistry of nature itself. It is an unusually large satellite, nearly a quarter of Earth's diameter, and it carries an extraordinary amount of angular momentum. Most planets in our solar system possess only tiny moons, or none at all. Mars, for instance, has Phobos and Deimos, small captured asteroids, barely able to maintain their form. They offer almost no stabilizing influence, which is why Mars's axial tilt wanders so dramatically, shifting between 10 and 60 degrees across time. The evidence of this instability is written into its surface ice caps that drift ancient rivers that dried long ago, a planet that never found equilibrium. It stands as a vision of what Earth might have become. How then did our planet escape such chaos? Most scientists believe the answer lies in a single colossal collision. Around 4.5 billion years ago, a planet roughly the size of Mars, known as Theia, struck the young Earth. The impact hurled molten debris into orbit, forming a ring of incandescent rock that eventually gathered into the moon. Because it was born from Earth's outer layers, the moon shares much of our planet's composition, yet it gained enough mass and angular momentum to profoundly shape Earth's long-term destiny. That impact may have created the very circumstances required for life. Not simply by giving us tides and the soft glow of night, but by fixing Earth's axis in a stable tilt from the beginning. Had Theia missed, we might not exist at all. It is a quiet kind of miracle. The moon does not warm the air or fill the oceans with oxygen. It does not harbour life or grow food, but it steadies the world, allowing life to unfold upon its stage. By preventing extreme swings of climate, it grants evolution the continuity to build complexity, to let forests spread, civilizations emerge, and ecosystems endure. It gives us time to adapt, to change, to survive. Even now, the moon's steady hand continues its work. Without it, climate models suggest Earth could transform beyond recognition in mere thousands of years. With it, our planet remains balanced in a delicate cosmic harmony that seems ordinary until you glimpse its fragility. So when someone dismisses the moon as dull, lifeless, or simply a dusty sphere, remember that this modest companion is the reason we are not extinct, the reason Earth is not a frozen spinning marble or a scorched wobbling furnace. The moon makes Earth what it is. Without it, our home might be uninhabitable. The moon does not merely orbit us, it anchors us. Look up tonight. That calm, familiar disk, always the same distance, the same luminous face feels eternal. Yet it was not always so. Long ago it was far closer, filling the sky like a radiant giant. In those days, Earth was a different world, its days just 5 hours long, its tides immense, its rotation dizzyingly swift. To understand why, we must return to the moon's birth, back to that titanic impact about 4.5 billion years ago. Theia collided with the early Earth, and the debris eventually gathered to form the moon, but it did not form where we see it now, a comfortable 384,400 kilometers away. At first it hovered astonishingly near only 20 to 30,000 kilometers above Earth's surface, roughly 14 times closer than today. From that distance it would have loomed 20 times larger in the sky, so vast you could have seen its craters and shadows with the naked eye. Yet, its proximity did more than change the view, it transformed the planet's behavior. The gravitational pull was immense, powerful enough to raise colossal tides, not just in the oceans but in Earth's molten crust. Mountains of rock rose and fell. The surface flexed and shifted in a constant gravitational struggle. The Earth and Moon were locked in a violent cosmic dance, exchanging energy, reshaping one another moment by moment. One profound effect was on Earth's rotation. Today our planet turns once every 24 hours, but back then it completed a rotation in just 5. A full day from sunrise to sunrise lasted only a fifth of what we now know. The sun would race across the sky, nights and days rushing past in breathless succession. Winds howled faster, storms swept the globe, and the young Earth spun in overdrive. But tides in their friction began to slow this furious spin. As the Moon tugged on the oceans, it raised a bulge that lagged slightly behind its orbit. Because Earth rotated faster than the Moon moved, the bulge pulled forward, giving the Moon a small push, adding to its angular momentum and driving it outward into a wider orbit. Energy, however, must balance. As the Moon drifted away, Earth's rotation slowed. It continues to do so even now. The Moon is receding from us at roughly 3.8 centimeters per year, the pace of growing fingernails. It seems trivial, yet over millions of years, it changes everything. Geological layers, coral growth rings and tidal sediments still record this ancient rhythm, the quiet story of how a violent beginning became the balance that sustains us today. Earth once spun faster, and the Moon lingered much nearer. We can trace this celestial rhythm through deep time. About 620 million years ago, a day on Earth lasted only 21.9 hours. 900 million years ago, roughly 18 hours. Travel back 4 billion years, and our planet rotated so quickly that a single day passed in merely 4 to 6 hours. If this gradual trend continues far into the future, Earth and the Moon will eventually reach a point of mutual tidal locking. Then Earth would forever show one face to the Moon, just as the Moon does to us today. But that moment is still distant. For now, the Moon drifts away ever so slowly, like a companion in a grand cosmic waltz. Each year it climbs a little higher, easing Earth's rotation, stretching our days by fractions of a second. The change is imperceptible to us, but on geological timescales it is profound. And this steady retreat, this ancient movement, may have been vital for the emergence of life itself. Those wild tides of the early Earth likely churned the oceans, blending heat and nutrients, stirring the chemical seas that would one day awaken into living forms. As Earth's spin slowed, the climate became gentler, days grew longer, and biological rhythms found their cadence. The Moon shaped not only the oceans, but the very pulse of life. That pale and tranquil orb above us, seemingly eternal, is in fact in constant motion. Long ago it was so close that it would have bathed the night in light, almost as bright as a second sun. It slowed the turning of our planet, stretched our days, steadied our weather, and perhaps even made life possible. We now live in the aftermath of that cosmic dance, on a world balanced by something once fierce, once monstrous, now serene. The Moon once dominated the sky, and in its gradual withdrawal, it gifted Earth something beyond measure, time itself. It feels like a singular companion, our ever-present neighbour, circling in silence. It is so woven into our experience that we call it simply the Moon, as though no other could exist. Yet what if that assumption is wrong? What if in the ancient past, Earth had 2 moons instead of 1, and what if that second moon did not vanish, but became part of the one we see today? This is not fantasy, but a genuine scientific hypothesis, proposed to explain one of the Moon's most puzzling features, why its far side is so peculiar. The near side, always facing Earth, is marked by vast dark plains called Maria, ancient lava fields that filled low basins, giving rise to the familiar face we recognize. The far side, by contrast, is rugged, heavily cratered, and almost devoid of Maria. Its crust is thicker, its terrain more chaotic. To understand this stark contrast, scientists Martinuzzi and Eric Assef proposed the double moon hypothesis in 2011. In their model, Earth once possessed two moons, the main moon we know and a smaller companion roughly 1,000 kilometers wide. Both were born from the same debris cloud left after a colossal impact with a body known as Theia, the event that originally formed the moon. For millions of years, these two moons coexisted in a delicate gravitational balance. But such systems are inherently unstable. Eventually, the smaller moon spiraled inward toward its larger sibling. The collision that followed was not catastrophic, but rather a slow, low-speed merger, something like a cosmic pancake, gently landing. The theory suggests that instead of shattering the larger moon or carving a massive crater, the smaller one spread itself across one hemisphere, most likely the far side, creating a thickened layer of crust and mountainous terrain. This would account for the moon's asymmetry. Its far side is 10 to 15 kilometers thicker than its near side, an enormous difference that has long confounded scientists. Computer simulations support this idea. Models show that two moons in shared orbit could merge if the smaller one struck the larger at a shallow angle and a speed below 3 kilometers per second. That is slow in cosmic terms, gentle enough to fuse rather than destroy. Such a merger could redistribute rock across one side, forming the highlands we see today. Although the hypothesis remains under debate, it elegantly ties together several of the moon's mysteries: the uneven crust, the scarcity of Maria on the far side, its elevated topography, and the curious internal layering revealed by seismic and gravity data. The second moon, if it truly existed, is gone now. No separate core, no debris field, only its geological fingerprints pressed into the face of its larger twin. And since this would have occurred over 4 billion years ago, proving it may forever remain beyond our reach. To truly test the theory, we would need samples from the far side's highlands, examined with extraordinary precision, searching for chemical traces that might reveal the truth. And yet the notion of a vanished companion to our moon is not as outlandish as it sounds. Planetary systems are restless places full of collisions and captures. Mars may once have possessed other moons. Around Saturn and Jupiter, swarms of wandering fragments are forever being drawn in and cast away. Even Earth occasionally acquires fleeting moons, small asteroids that drift into orbit for a time before slipping back into the dark. So the suggestion that our world once had two natural satellites born from the same primordial impact remains well within the boundaries of possibility. Some scientists even propose that multiple moons may be a natural step in the life of a planet. After a colossal collision, the scattered debris does not always unite into a single sphere. Instead, it forms a cloud of fragments, some coalescing, some escaping, others lingering in delicate orbits before colliding and vanishing. Perhaps our moon is not the sole survivor of that ancient chaos, but rather the final product of a cosmic merging, the last remnant of a sibling world absorbed into its face. That collision, slow and immense, erased one moon and sculpted another. The smooth plains we call Mariae and the rugged highlands may whisper of two worlds that became one fused in silence billions of years ago. If so, then the second moon never truly disappeared. It remains within, buried beneath crust's myth and memory. The moon feels eternal to us. It governs our tides, illuminates our nights, marks the rhythm of our calendars. It has gazed down upon every civilization that has ever existed. And yet, across the ancient world, in myth and story, there are tales of a time before it hung in the heavens, an age when the night sky was different, when there was no lunar light. Such legends are not confined to one people, but echo through many, scattered across continents and centuries long before the rise of science. Could these be mere metaphors or faint memories of a sky that truly lacked a moon? The Greeks had a word for it, proserpine, meaning before the moon. The Arcadians who lived in the mountains of central Peloponnese were said to be people of that era. Aristotle himself mentioned them, describing a race who dwelled upon the earth before the moon shone above. To them, the moon's appearance was not symbolic, but an event that changed the sky. Far across the ocean, the Muisca people of Colombia told a similar story. In their tradition, there was a time when the moon was absent and the world descended into chaos. Then a goddess, Kia, rose into the heavens and became the moon, restoring harmony and order. The Zulu of southern Africa spoke too of a night before the moon, when darkness reigned until two divine brothers, Wainain and Pangu, rolled a glowing orb into the sky. Among the Inuit old tales describe the moon as a being once human pursued or transformed, a new light recently added to the heavens. How should we understand this? It is tempting to dismiss such stories as imagination or allegory. Yet it is remarkable that so many distinct cultures, divided by oceans and epochs, shared this idea that the moon was not always there. The sun and stars were considered eternal, the moon somehow was not. Some researchers think these legends might preserve echoes of deep time memory fragments passed down orally by people who watched the sky thousands of years ago, perhaps even before recorded history began. Others see them as mythic accounts of great celestial events, eclipses, comets, meteor showers, interpreted as the birth of the moon. And then there are those who go further, proposing that early humans, or even pre-human ancestors, may have lived in an epoch before the moon formed. They point out that our satellite is thought to have arisen 4.5 billion years ago, long before intelligent life. The timelines seem irreconcilable. But if they argue the moon's creation happened later than we believe, through a delayed collision or a captured orbit, then perhaps humanity's distant ancestors witnessed its arrival. This is speculative, well beyond accepted science. The prevailing view remains that the moon was born soon after Earth from the impact with Theia. No solid evidence suggests a later formation. Still, the moon's near-perfect orbit, its synchronized spin, its peculiar composition, and the speed of its drift away from us continue to remind us that we do not yet fully understand its story. Some suggest that the old tales may speak of an age when the moon was only a faint presence in the sky. Perhaps it was veiled by cosmic dust, or had not yet settled into the graceful orbit we know today. Or maybe those myths were born in the aftermath of great celestial spectacles, a vast eclipse or a blazing meteor that made the heavens seem newly reborn. Yet even in the accepted story of geology, there was a time when Earth existed without its companion. In the first 30 to 100 million years after the planet formed, if a thinking mind had looked up then, which none did, it would have seen a night without a moon. Maybe these ancient stories are echoes of that profound truth. The moon is not eternal. It had an origin. It arrived. No matter how those stories began, one thing is clear. Across the world, humanity preserved the belief that the moon appeared, emerged, or was fashioned in a way that marked a turning point in cosmic history. And perhaps that belief is not far from reality, because even though the moon was born billions of years ago, its presence transformed the Earth. The tides, the rhythm of climates, fertility, the night sky, our myths and our dreams all shifted beneath its influence. A time before the moon is not something we can witness, but perhaps it is something our ancestors intuited, remembered, or imagined deep within. And in that imagining, they may have captured a fragment of truth that science is still unfolding. The moon is not just another object in the sky. It is a phenomenon, a story that began somewhere in time and left its mark on the evolution of life. When we imagine the moon, we think of silence, a desolate world under a black sky where the stars never flicker and no wind stirs the dust. And in many ways that is true. The moon has no air we can breathe, no clouds, no weather. Yet here lies the surprise. It does have an atmosphere. It is nothing like ours. So thin, so ephemeral, that scientists once failed to notice it. It is called an exosphere, one of the strangest and most fragile features of the lunar world. So what exactly is an exosphere? Unlike Earth's thick, layered atmosphere where pressure, temperature and composition shift with altitude, an exosphere is a tenuous cloud of solitary particles barely clinging to the surface. There is no real air, no meaningful density, no pressure as we understand it. It is not a flowing fluid like the air we breathe, but a ghostly plasma where atoms and molecules are so far apart they almost never collide. If Earth's atmosphere is like an ocean, the moon's is like a mist, so fine that each particle can travel kilometers before meeting another. In total, the moon's exosphere weighs only about 10 metric tons less than a single school bus spread thin across the entire moon. Even in its densest regions, there are only about 100 molecules in each cubic centimeter, compared to the 10 billion in the same space at sea level on Earth. That makes it 1 trillion times thinner than what surrounds us, a near perfect vacuum. And yet, it exists. It was discovered partly through instruments left behind by the Apollo missions and later confirmed by robotic explorers. Within it are traces of helium from the solar wind argon, slowly escaping from the lunar interior through radioactive decay, and unexpected elements like sodium and potassium lightly hurled upward by micrometeorite impacts and sunlight itself. There are also hints of hydrogen, oxygen, and even fleeting molecules of water vapor, perhaps created by the dance between solar particles and lunar dust. Unlike Earth's atmosphere, which is bound tightly by gravity and constantly in motion, the Moon's exosphere behaves more like a ballet of particles leaping and falling. Each one follows a graceful arc, bouncing off the surface, gaining energy and drifting again. There are no winds, no storms, only a silent choreography unfolding in slow motion. The term exosphere usually refers to the outermost layer of a planet's atmosphere, the boundary where atoms begin to drift into space. But for the Moon, the exosphere is the whole story. No deeper layers, just this veil of particles above a barren world. And this fragile shroud is not static. During the lunar day, sunlight heats and releases atoms. At night, they cool and settle. Tiny meteor strikes send bursts of gas and dust upward, creating short-lived clouds that fade again into emptiness. And then there is the strangest detail of all: the Moon has a sodium tail. Because sunlight pushes on sodium atoms through radiation pressure, they are slowly blown into space, forming a tail that extends for thousands of kilometers, always pointing away from the sun. Around each new moon, this invisible plume sweeps across Earth, a spectral trace that only special telescopes can see, a faint river of lunar light moving through the darkness. All of this matters far more than it seems. For as we prepare to return to the Moon, every step we take, every engine that fires, every dust grain disturbed, will change that delicate exosphere forever. Rocket exhaust, landers, rovers, and even the marks of our boots can lift tiny particles from the lunar surface, disturbing a system that exists in delicate balance. Unlike the robust atmosphere of our own world, the Moon's exosphere is fragile, easily transformed by the slightest intrusion. Some scientists fear that our exploration might alter it forever, perhaps without even realizing it. That is why upcoming missions, such as the Artemis program and a new generation of lunar orbiters, are carrying instruments built to observe this ghostly envelope in greater detail. By studying its makeup, its motion, and the story of its birth, we can uncover clues not only about the Moon itself, but also about other airless bodies across the solar system: Mercury, asteroids, and even planets orbiting distant stars. So although the Moon lacks an atmosphere as we usually define it, it possesses one in a far more ethereal and extraordinary form. An atmosphere of solitary atoms, fragile reactions, and invisible forces stretching into the void. It is one we cannot see or touch and can barely measure, yet it exists, thin as a whisper, shifting constantly, another quiet reminder that the Moon still has mysteries to share. A place we thought we knew, revealing once again that it defies our expectations. When we think of dust, we imagine something soft, harmless, easily brushed away. But on the Moon, dust becomes something far more formidable. It is not just a minor inconvenience. It is one of the greatest hazards awaiting future explorers. So dangerous that it can erode machinery, tear at spacesuits, and threaten the lungs of those who breathe it. The Moon's surface is coated in a powdery layer known as regolith. From a distance it resembles dry beach sand, but up close it is utterly alien. This dust has not been shaped by wind or water, for there is no air to wear its edges smooth. Instead, it is forged by countless micrometeorite impacts that shatter rock into sharp, jagged fragments. Each grain is a splinter of broken glass, rough, angular, and charged with static electricity from unending solar radiation. When the Apollo astronauts first set foot upon the lunar surface, they met this adversary immediately. The dust clung to everything: boots, gloves, visors, and cables. It crept into seals and joints impossible to keep out. No matter how carefully they brushed themselves before entering the lunar module, it followed them inside, where it refused to leave. The particles wore down equipment faster than expected. They scratched visors, jammed zippers, and caused the joints of spacesuits to grind. Some astronauts even noticed the scent of gunpowder inside the cabin, a metallic, acrid smell born from the freshly reactive dust. And because the moon has no atmosphere, that dust never weathers or oxidizes, it remains chemically aggressive, ready to react the instant it touches air or moisture. But it was not only the equipment that suffered. Inhaling lunar dust, even in tiny quantities, poses a serious risk. During Apollo 17, astronaut Harrison Schmitt experienced what he called lunar hay fever after breathing in dust that had drifted into the cabin. His sinuses swelled, his throat itched. The symptoms faded, but the warning was clear. If short-term exposure could irritate, what might long-term exposure do? Scientists now fear that lunar dust could act like asbestos. Its microscopic shards might lodge deep within lung tissue, causing inflammation, scarring, or illnesses akin to silicosis, the disease that miners and construction workers face after breathing fine silica for years. Once these particles enter the body, they are nearly impossible to remove. Over time, the damage could become permanent, even leading to cancer. Because lunar dust is so fine, some grains even reduced to nanometer scale, it is nearly impossible to filter completely. It can drift through spacecraft on clothing or invade life support systems. On Earth, gravity and moisture pull dust down to the ground, but on the moon it simply lingers, clinging to everything it touches. Modern scientists take this danger seriously. NASA continues to study lunar regolith using both Apollo samples and synthetic versions known as lunar simulants. These investigations reveal that the dust is not only abrasive, but also electrically charged, capable of sticking to anything, even lifting slightly from the surface when sunlight floods the lunar day. Astronauts once described a strange horizon glow after sunset, likely caused by levitating dust particles. Instruments left on the moon have shown signs of slow decay over the decades, their solar panels fading, their sensors clouding, their moving parts seizing all victims of relentless dust. And that is before considering what will happen when humans return to stay for weeks or even months. As agencies plan the next era of lunar exploration, dust control has become one of their most urgent challenges. Possible solutions include electrostatic brushes that repel charged grains, self-sealing suit fabrics, and airlock-like dust docks that let astronauts clean themselves before entering their living quarters. The purpose is to reduce exposure for both the machines and the people who must inhabit and operate in this alien landscape. Because although the moon seems serene from its distance of 384,400 kilometers, its surface conceals countless microscopic threats waiting to invade every mechanism we place there. The same dust that once preserved the footprints of explorers could one day dismantle the very tools that follow them, or harm the next generation of those who dare to use them. The moon may be silent, motionless and cold, but its dust is vibrant with menace, sharp as glass, toxic as smoke, and as unwelcoming as the deepest regions of space itself. For a world that appears frozen and lifeless, the moon has a remarkable talent for behaving strangely, not only in its geology or chemistry, but in its appearance. For centuries, astronomers have witnessed odd flickers, glimmers, and bursts of light rising from its grey plains. These were not stars nor passing comets. They were quick, fleeting, and undeniably lunar in origin. Both amateur and professional observers recorded them long before satellites or orbital stations existed, and even today, no one, not even the most meticulous engineers at the Space Agency, can provide a complete explanation. They are called transient lunar phenomena, or TLPs, an official title that hides the truth of our ignorance. They reveal themselves as sudden blinks of brightness, colours, or mist that linger for moments before fading away. At times they pulse, at times they shimmer, sometimes resembling a solitary firefly flickering across the barren surface, and yet they are real. They have been chronicled for more than 1,000 years. The earliest record dates back to the year 1065, when monks in Canterbury described a glowing body gliding across the face of the moon. Over the centuries, more accounts emerged. In 1178, 5 monks claimed they saw the upper horn of the moon split apart, releasing fire sparks and molten embers. In 1787, the renowned astronomer William Herschel wrote about bright flares and what appeared to be volcanoes glowing on the lunar terrain. At that time, many scientists believed the moon might still breathe with geological life, perhaps even capable of supporting some primitive form of environment, a belief that lingered well into the 20th century. As telescopes improved, reports of these strange events continued. In 1958, the Soviet astronomer Nikolai Kozyrev observed a reddish glow near the crater Alonsus, interpreting it as a release of gas. His spectrographic measurements revealed traces of carbon-based compounds, evidence that suggested a volcanic-like reaction, though others doubted it. The moon, by the standard model, was long dead, and yet the lights persisted. In 1963, the Space Agency compiled a study listing 579 verified TLP sightings, gathered from different observers over many decades. Some were photographed, others confirmed with separate instruments. The most active regions were craters such as Aristarchus, Plato, and Copernicus sites, marked by unusual reflectivity and curious thermal readings. Among these, Aristarchus stands apart. It is the most brilliant of the large craters, its surface gleaming more than it should, as though it remembers sunlight differently. Dozens of TLP events have been linked to it. Astronomers have described it as flickering, throbbing, even radiating a pale blue aura. No reflection from Earth can account for it, and this is no trick of the eye. Orbiting spacecraft have detected measurable energy emissions from that same location. So what might create these ghostly lights? Some propose that the moon is not entirely inert. Residual gases like radon or argon, sealed beneath its crust by ancient volcanic activity, might occasionally escape. When they encounter sunlight or collide with charged solar particles, they could form brief luminous veils across the ground. Others point to electrostatic forces. Without an atmosphere, the moon is endlessly struck by solar wind charging its dust, until it hovers and scatters light in uncanny ways, particularly at lunar dawn or dusk, when the sun's low rays ignite it into momentary gleams. There are also the countless meteor strikes, hundreds every year, each one capable of producing short-lived flashes of heat and light, possibly explaining some of the phenomena, though not the repetition at the same craters over centuries. Another idea lies in the piezoelectric properties of the moon's rocks. Moonquakes, which we now know occur, might cause friction among crystalline minerals, generating electrical discharges, tiny lightning bolts erupting from within. None of these explanations fits all the evidence. Some lights occur on the far side, some during periods of complete stillness. Even after decades of scrutiny, no high-resolution camera in orbit has yet captured one happening in real time. They always seem to elude us just out of reach. Yet the mystery endures. The Lunar Reconnaissance Orbiter continues to watch the most active sites, while telescopes on Earth patiently wait through every lunar night, hoping to glimpse the next pulse of light from that silent world. There are even projects underway to build fully automated telescopes, whose only mission is to watch the lunar surface, capturing images every few milliseconds in search of brief, fleeting bursts of light. Because here is the truth. The moon is meant to be still, airless, devoid of life or movement, a relic of geological silence. Yet these occasional lights whisper of motion, of energy, of something quietly unfolding in that darkness. Perhaps small, perhaps subtle, but undeniably real. And that uncertainty, that hint of the unknown, keeps the mystery alive. For though the moon has surrendered much of its story, it has not told us everything. Somewhere within its vast frozen plains, beneath its scarred craters, there are places where things still stir, still glimmer for a heartbeat, as if to remind us that the moon has not finished surprising us. It is not simply a rock suspended in the sky. It is an active enigma, winking at us literally from the shadows. It sounds like the stuff of science fiction, the notion that our moon might be hollow, not figuratively or partially, but literally hollow, or at least laced with enormous caverns beneath its outer crust. To most, the idea borders on absurdity, even comedy. And yet the roots of this theory are grounded in real data, seismic readings, unanticipated results, and a series of strange anomalies that refuse to disappear. Let us begin with the clue that started it all. The moon rings like a bell. In 1969, during the Apollo 12 mission, astronauts installed seismic sensors on the lunar surface. Later, once they had returned to their module, they intentionally crashed the discarded lunar ascent stage onto the moon to record the impact. It struck with a force equivalent to roughly 1 ton of trinitrotoluene. The result was astonishing. The moon vibrated, but not in the way Earth does. Earth, with its molten core and tectonic restlessness, quivers and then quickly quiets. The moon, however, resonated for over an hour. According to one report from NASA, the moon rang like a bell. Not literally, of course, but the vibrations were unusually consistent and enduring, as though the energy had nowhere to go. A few years later, Apollo 13 repeated the experiment unintentionally. When the mission was aborted, the Saturn Phoebe rocket booster slammed into the lunar surface with even greater energy. Once again, the seismic recorders picked up a deep, sustained echo that lasted 3 hours and 20 minutes. No one at NASA claimed the moon was hollow, but the readings were perplexing. A solid uniform sphere should not behave that way. Something within the lunar interior was not acting as predicted. This prompted some scientists to suggest that the moon's makeup might be peculiar, perhaps a thin crust surrounding a rigid shell with a less dense interior that lets seismic waves bounce rather than fade. That is not the same as being hollow, but it planted a seed for speculation, and speculation inevitably took root. In the 1970s, Soviet researchers Mail Vazin and Alexander Bakov published a provocative paper titled "Is the Moon the Creation of Intelligence?" They proposed that the moon might not be natural at all, but an artificial satellite, possibly hollowed out by unknown entities and placed in Earth's orbit. Their reasoning was bold. The orbit seemed too precise, the surface composition too strange, the crust unusually hard, and the seismic ringing too suggestive of emptiness. This was far from mainstream science, but it captured imaginations. The hollow moon theory quickly spread through fringe communities. Some claimed the moon was a colossal spacecraft sheathed in rock. Others saw it as a dormant alien base. Still others imagined its hollowness as the reason Earth's rotation remained stable, as though it were engineered to act as a counterweight. Yet when we pull back from the edge and look through the lens of modern science, a clearer picture emerges. In 2011, NASA's Grail mission, the Gravity Recovery and Interior Laboratory, mapped the moon's internal structure with remarkable precision. The data revealed a heavily fractured crust, a mantle less dense than anticipated, and deep complex layers but no hollow center. The evidence pointed instead to a stratified world with a small solid inner core and a partially molten outer one, echoing Earth's structure, but less dynamic. Still, the mystery of the moon's unusual resonance remains. Its low seismic attenuation, the way it poorly absorbs shock, continues to puzzle researchers, and that bell-like vibration has yet to be fully explained. Some believe the secret lies in the moon's extreme dryness and rigidity. Without water to help scatter energy, seismic waves travel much farther. Imagine striking a bell made of granite rather than bronze. The sound lingers differently because of the material itself. Dry rock transmits energy with extraordinary clarity compared to the soft, damp rock beneath our feet on Earth. So perhaps the moon rings not because it is hollow, but because it is profoundly dry and astonishingly rigid. Others point to its low iron content as part of the story. Unlike our planet, the moon does not possess a dense metallic core. Because of that, it experiences less gravitational compression, less internal motion, and a crust that behaves more rigidly. This also explains the absence of a global magnetic field, which would require a spinning molten heart. And yet the hollow moon idea lingers on, driven by something deeper than data, by that old, haunting sense of cosmic strangeness. For the moon is by any measure peculiar. Its diameter is roughly 400 times smaller than that of the Sun, and it happens to be about 400 times closer to Earth. This coincidence allows it to cover the Sun with astonishing precision during an eclipse. No other moon in the solar system performs such a perfect alignment. Chance perhaps, but an uncanny one. Then there is its orbit. Almost circular, slightly tilted, and enormous when compared to its host planet. No other terrestrial world carries a satellite so large in proportion. Some scientists even argue that Earth and the Moon should be classed as a binary planet system rather than a planet with a moon. So no, the moon is not hollow, but it is certainly strange. Strange in its form, in its composition, and in its conduct. Born in a cataclysmic collision, it somehow became vital to Earth's stability, and yet it still confounds us with the faint echoes from its interior. The hollow moon theory may not survive modern scrutiny, but the observations that inspired it, the ringing, the seismic oddities, the unexplained resonances, remain reminding us of a simple truth. We do not know the moon as well as we think we do. Even more than 50 years after the first human footprints marked its surface, it continues to guard its mysteries. Some of them whisper back long, slow, and uncanny, as if something were knocking from within. For most of our history, we gazed upward and wondered. Then, in the 1960s and 70s, we went there, and the moon became a milestone rather than a mystery. But in recent years, something unexpected has happened. As much of the world turned its eyes toward Mars, China quietly returned to the moon, not merely orbiting, but landing, driving, digging, and bringing pieces of that ancient world home. What they found was not just dust and stone, it was something unfamiliar. The Chang'e 5 mission, launched in late 2020, was the first to return fresh lunar samples in more than 44 years since the Soviet Lunar 24 mission of 1976. Chang'e 5 touched down in a region never before visited, known as Mons Rumca, a volcanic dome complex within Oceanus Procellarum, the Ocean of Storms. This landing was deliberate. Unlike the Apollo missions, which explored older terrain, this site was chosen for its youth, about 1.2 billion years old, a billion years younger than the Apollo samples. The goal was to fill a missing chapter of lunar history, but what they discovered went beyond expectations. Within the collected material, scientists identified an entirely new mineral in 2022 named Changesite Y. It is a phosphate crystal formed in basaltic lava flows, similar in structure to minerals found in Earth's rare earth regions, yet this specific arrangement had never been observed before, not on Earth, not on the moon. That alone was remarkable, revealing new clues about how the moon cooled and evolved. But there was more. Embedded in the same samples were traces of helium-3, a rare isotope scarcely present on Earth but possibly abundant on the moon. For decades, scientists have speculated that helium-3, implanted by the solar wind and locked within the lunar soil, could serve as a potential fuel for nuclear fusion, the clean energy that might one day power entire civilizations. Helium-3 is unimaginably rare and costly here, yet the moon's fine sunlit dust could contain vast reserves. And this is no longer just theory. The Chang'e 5 samples confirmed measurable amounts of helium-3, especially within the finest grains, long bathed in solar radiation. If harnessed, the moon could become the Saudi Arabia of fusion fuel, a treasure not only for science but for geopolitics. Still, the surprises did not end there. During analysis of the Chang'e 4 mission, the first rover to explore the moon's far side, Chinese scientists detected an unusual gel-like substance inside a small crater. It appeared glossy, viscous, and darker than the surrounding soil. Instruments revealed a glass-like structure, possibly born from the searing heat of a meteorite, impact that fused rock into something almost alien. It was not alive, not moving, but neither was it ordinary. Its true nature remains uncertain. Some researchers think it may be a kind of impact melt, breccia, shattered stone welded by heat, while others propose volcanic glass formed under extreme conditions. Either way, it is unique, something no Apollo mission ever found. And perhaps that is the most astonishing revelation of all. We thought the moon was finished, a story already told. But China's missions have shown that it is still a living archive, still holding secrets just beneath its surface, waiting for those who are willing to look again. And not only from a scientific point of view, but from an industrial, energetic, and perhaps even strategic one. The samples are still under careful study, and we have only just begun to understand them. Chang'e 5 returned merely 1.7 kilograms of soil and stone. In contrast, the Apollo missions brought back 382 kilograms in total, yet the Chinese samples come from an entirely different lunar region, shaped by a very different geological story. That difference makes them priceless. It feels as though we are opening a brand new chapter in a book written billions of years ago. And the story continues. China is preparing Chang 6, which will attempt another sample return, this time from the far side of the moon. If it succeeds, it will mark the first occasion that material has ever been retrieved from the moon's hidden hemisphere. That region is older, scarred by countless impacts, and far less volcanic than the side that faces us, which means the samples could hold stranger and more alien secrets. What might truly lie hidden in that lunar dust? Perhaps new minerals, maybe potential fusion, fuel, molten glass forged by ancient cosmic collisions, and possibly even things beyond our imagination. The moon may seem a silent, lifeless rock, yet beneath its surface lies a time capsule, preserving the solar system's earliest history and perhaps the resources that could one day power human civilization. Through these missions, we have learned that the moon is not just ancient, it is diverse, active in subtle ways, and still full of surprises. And it reminds us of a truth we should never forget. Exploration still matters, because lifting the next stone, even 384,000 kilometers away, can reveal something no one on Earth has ever seen. And all it takes is a shovel, a rover, and the will to dig a little deeper. Imagine wandering through a desert, a mountain peak, or a frozen field in Antarctica and bending down to pick up a rock. You would never guess that it came from the moon. Not a souvenir from Apollo, not debris from a secret mission, but a natural fragment ejected from the lunar surface by a cosmic impact hurled through space and landing on Earth entirely by chance. As unbelievable as that may sound, it has indeed happened. And not just once. Scientists have confirmed that dozens of meteorites found on Earth are lunar in origin. They are natural travelers thrown into space by colossal asteroid strikes, surviving the emptiness of space and finally falling to Earth, where they rest unseen for thousands, sometimes millions of years. So how does this extraordinary journey begin? It starts with an impact of immense force. When a meteoroid strikes the moon's surface at tremendous speed, the energy released is vast. Because the moon has no atmosphere to slow the incoming object, the collision is violent and unrestrained. That explosion can hurl fragments from the crust into space, and if those fragments reach the moon's escape velocity, about 2.4 kilometers per second, they break free from its gravity and begin their voyage through the solar system. Most of this material drifts endlessly, captured by the sun's pull, burning up in planetary atmospheres or colliding with other celestial bodies. But a tiny, very fortunate fraction finds its way to Earth. Since the moon lies relatively close, only around 384,000 kilometers on average, its ejected debris can reach us in days or weeks. And because lunar material travels slower than most asteroids from deep space, it often enters Earth's atmosphere at lower velocities, giving it a better chance to survive re-entry intact. When it lands, it looks like any other meteorite, dark, dense, and scorched from its descent. For years, scientists had no method to determine where such rocks came from. But that changed in the 1980s. With new analytical techniques, geologists noticed that certain meteorites had distinct chemical and isotopic fingerprints, especially oxygen isotopes, that matched the Apollo samples exactly. That was the first great clue. Later mineral composition, age analysis, and trapped gas studies confirmed it. Some meteorites contained tiny bubbles of gas, identical in composition to the lunar atmosphere, measured directly on the moon. These were not just similar to moon rocks, they were moon rocks. Today, over 400 lunar meteorites have been identified, discovered in more than 24 countries. Some were found in the arid deserts of northwest Africa and Oman. Others lay on the frozen plains of Antarctica, where the dark stones stand out sharply against the bright ice. That is why Antarctica remains a prime hunting ground for these space relics. The cold, stable environment preserves them for millennia, and the stark contrast makes them easier to spot. And perhaps most remarkable of all, some of these natural moon rocks are older than anything brought back by the Apollo astronauts. While those missions sampled specific areas of the near-side lunar meteorites, come from random locations across the surface, including places humanity has never seen directly, they have granted us a more profound and expansive view of lunar geology, offering glimpses into regions of the moon that had never before revealed their secrets up close. Yet with these revelations come new mysteries. One such enigma lies within a lunar meteorite known as S. Alima 169, discovered in Oman in the year 2002. Its unusual chemical signature hints that it may have originated deep within the lunar crust, or perhaps even from the mantle itself, whispering clues about the moon's inner architecture, clues that surface samples alone could never unveil. And then there is the philosophical turn. For centuries, the idea of possessing a fragment of the moon belonged to poets, dreamers, and the realm of imagination. But now we understand that fragments of the moon have been falling to Earth since time immemorial, unseen, scattered across deserts, fields, and mountainsides, patiently awaiting discovery. Consider this. At this very moment, somewhere on our planet, another piece of the moon might lie half buried in a dune, trapped within a glacier, or resting unnoticed atop a rooftop after a fiery meteor blazed through the sky. Someone could stroll past it, oblivious, just inches away from a 4-billion-year-old traveller that survived the inferno of re-entry and landed softly on Earth. It changes the way we feel about our celestial companion. The moon ceases to be a distant, untouchable light in the heavens and becomes instead a tangible neighbour, one that occasionally shares fragments of itself with us, quietly, almost tenderly. It is a world that leaves traces behind, like keepsakes, scientific gifts, reminders that the cosmos is forever in motion, forever exchanging, forever leaving hints for those who know where to look. Yes, some pieces of the moon reside here on Earth, having journeyed to us entirely through the workings of nature. No rockets, no rovers, only gravity, collision, and time. The moon may seem drenched in unending sunlight from our earthly vantage, its face glowing serenely night after night. But if you were standing there, particularly near its poles, you would witness a far harsher truth, a landscape sculpted by extremes, where light and darkness divide the terrain into eternal brilliance and endless shadow. Within those shadows lie places untouched by the sun for billions of years, regions so cold, so pristine, that they rank among the most frigid environments in the entire solar system. These are the permanently shadowed regions, or PSRs. They exist primarily near the lunar north and south poles, where the sun hovers perpetually at the horizon, never climbing high. Because the moon's axial tilt is only about 1.5 degrees, compared to Earth's 23.5 sunlight, there barely shifts throughout the lunar year. Deep craters cast shadows that never retreat. Since the moon's fiery formation, some of these crater floors have never seen daylight, not for a single heartbeat of time. Within those frozen hollows, temperatures plunge to astonishing depth. NASA's Lunar Reconnaissance Orbiter recorded the floor of the crater Hermit at approximately minus 410 degrees Fahrenheit, colder than the dwarf planet Pluto, among the lowest temperatures ever measured anywhere in the solar system. And what lies hidden in that darkness? In a single word, ice. Not a trace, but perhaps billions of tons. Scientists believe these PSRs act as natural cryogenic vaults, preserving water molecules delivered by comets, asteroids, or even the gentle accumulation of hydrogen and oxygen from the solar wind. Once water reaches these airless, sunless basins, it remains trapped, no atmosphere to let it escape, no sunlight to thaw it. It endures frozen and ancient. NASA confirmed the presence of this ice through multiple lines of evidence. The L-Cross mission, which intentionally impacted the moon's south pole in 2009, detecting water vapor in the plume that rose from the collision. The Moon Mineralogy Mapper aboard India's Chandrayaan-1 spacecraft, which identified spectral traces of ice in permanently shadowed regions, and thermal and neutron measurements from orbiters revealing zones rich in hydrogen, strongly implying water locked beneath the surface. This is far more than a scientific curiosity. It may redefine our future in space. Lunar water means drinking water for explorers, oxygen for life support, hydrogen for fuel resources that could transform the moon into a refueling outpost for deeper cosmic travel. The permanently shadowed regions could become natural way stations, gateways for humanity's next great journeys. That is why NASA's Artemis missions focus on the lunar south pole, not for its beauty, but because those shadows may conceal the most valuable resource beyond Earth. Yet reaching them will test the limits of our ingenuity. These craters are immense, dark, and unimaginably cold. Solar-powered machines falter without light. Communication is disrupted by the harsh terrain. Batteries freeze. Metals grow brittle. And still somewhere in that eternal night, beneath the frost of unbroken centuries, the promise of discovery waits. These landscapes are more alien and more extreme than any world the human species has ever touched. Yet even now, plans are unfolding. The National Aeronautics and Space Administration is preparing to send the Viper rover, the Volatiles Investigating Polar Exploration rover, within the next few years. It will be a specialized robotic explorer built to venture into these perpetual shadows, to drill deep into the lunar soil and test for traces of water, measure its depth and uncover its composition. If it succeeds, it will represent humanity's first true entry into these ancient, unlit sanctuaries regions that have not known the touch of sunlight since before the time of dinosaurs, perhaps even before multicellular life began. Imagine that. These are places that have remained in darkness since the moon first solidified, when Earth itself was still a world of fire and chaos, when life was nothing more than chemistry stirring in the oceans. Inside those frozen shadows may lie ice older than any glacier on Earth, holding secrets about the origins of water in the solar system, perhaps even about the molecules that led to life itself. They are like fossils of time preserved, not only by temperature, but by the stillness of history. So although the moon glows softly in our sky, luminous and familiar, it hides deep, genuine darkness in its polar craters, real shadows we have never entered, places that could shape the destiny of future missions, and paradoxically, places that might sustain life, not life native to the moon, but life carried from Earth, our own. In a sense, the moon still guards its unlit corners, ancient, silent, cold, and full of promise. For thousands of years, humanity believed that moonlight was cold, not merely in the poetic sense of pale or ghostly, but physically cold. It was thought that the light of the moon could cool whatever it touched, that it might spoil food, wither plants, even make a person ill. Some ancient writings warned against sleeping under moonlight, claiming it could bring fever, blindness, or madness, and strangely enough, people once tried to prove it. Let us pause. Today we understand that moonlight is simply sunlight reflected from the lunar surface. It is not a separate form of illumination, it carries no special cooling energy, and it emits no radiation of its own. The moon reflects only about 12% of the sun's rays. If anything, moonlight adds the faintest touch of warmth to the night air rather than chill. But before the age of modern physics, light itself was a mystery. In the ancient world, Aristotle and his followers taught that celestial bodies influence nature not only through gravity, but through vital energy, that the moon governed moisture, health, and even the human mind. The word lunatic comes from the Latin word for moon. It was once believed that the moon's phases could literally drive people to madness. This was not metaphor. It was accepted medical thought for centuries. When observers noticed that the moon often hung high in the sky on cold, dewy nights, particularly around the full moon, they made a simple connection: moon means cold. Through the Middle Ages, that idea grew into folklore and then into pseudoscience. Some physicians claimed that moonlight could cause meat to rot faster or milk to sour. Gardeners were told not to gather certain herbs under its glow. Others warned that moonlight could sap vitality from the sleeping body, especially if it fell upon the face. There were even beliefs that long exposure could bring on moon sickness, fatigue, confusion, or insanity. This was not merely superstition. Even during the Age of Enlightenment, scientists tried to measure the supposed chill of moonlight. In the 19th century, experiments were carried out using thermometers placed under moonlight and others kept in shadow. Some seemed to record a small temperature drop, reinforcing the myth that moonlight was cooling. But later analysis revealed the truth. The drop was caused not by the moon's light, but by heat radiating from the exposed thermometers into the cold night sky. The light was innocent. When real physics arrived with modern optics, the mystery dissolved. Moonlight carries only a minute fraction of the sun's power, around 0.1 lux, compared to 100,000 lux for direct sunlight. That is about 1/1,000,000th of the intensity. It is far too weak to alter the temperature of anything it touches. Skin, clothing, even ice remains unchanged. Yet the old belief persists. There are still fringe ideas claiming that moonlight possesses a cooling radiation or behaves opposite to sunlight. Amateur experiments with thermometers still appear to show things under moonlight as colder, but again the reason lies in the loss of infrared heat to the open sky, not in any property of the moon. This misconception led to curious detours through history. In the 1800s, moonlight was blamed for sleepwalking, bad dreams, even the twisting of plants. As late as the 20th century, it appeared in unorthodox medicine and theories linking lunar cycles to behavior, crime, and fertility. Some police departments once increased patrols during full moons, convinced that human behavior became more chaotic under its glow, a belief unsupported by data but deeply rooted in emotion. It is a testament to the moon's power over imagination. Its shifting light, its rhythm, tied to tides and time, makes it feel mystical and alive. So when our ancestors felt a chill beneath a bright full moon, it seemed entirely reasonable to think the moon caused it. And in one sense, perhaps they were right, not physically, but symbolically. Moonlight is cold not because it removes heat, but because of what it represents. It is not the light of fire, but the light of reflection. The moonlight carries no warmth, only a silent glow that feels like frost and stillness. Yet science tells us something different. Moonlight itself is neutral, a calm reflection of sunlight scattered through dust that drifts across space. It does not heat, nor does it cool. But for thousands of years we imagined it did, and that simple misunderstanding shaped beliefs, myths, and eventually the course of science itself. So the next time you stand beneath a full moon and feel the chill of night brushing your skin, remember this: it is not the moon doing it, it is the universe. But if you feel as though the moon is the culprit, you are not alone. Humanity shared that thought for around 2,000 years. The moon lies 384,000 kilometers away, and reaching it demanded the most extraordinary technology of the 20th century. It required the effort of hundreds of thousands of people and the expenditure of billions of dollars. When fragments of the moon were finally brought to Earth, real samples of another world, they were treated as sacred relics, pieces of cosmic history beyond price. Yet one of them somehow ended up forgotten in a garage, misplaced for decades. It sounds like fiction, but it is not. To uncover how that happened, we must travel back to the early 1970s, when the United States, proud of the Apollo triumphs, decided to share its lunar treasure. The administration of President Richard Nixon created what became known as the Goodwill Moon Rocks program. Tiny fragments of lunar material, just a few grams each, were mounted on plaques and sent to 135 nations and every one of the 50 United States. These small samples came from missions such as Apollo 11 and Apollo 17, sealed in transparent globes and displayed beside national flags that had journeyed to the moon. It was meant as a symbol of friendship, unity, and scientific wonder. But over time, something strange happened. Many of these Goodwill Moon rocks vanished, lost, stolen, misplaced. Some were traded on the black market for millions. Others disappeared into private collections. A few were believed destroyed by disasters or conflict. No one knows exactly how many are gone, but more than half are thought to be missing. One of the most famous cases involved the moon rock presented to Honduras. This particular fragment came from Apollo 17, the final Apollo mission. In the 1970s, it was gifted to the Honduran government, but at some point it disappeared. Not into a museum archive, but into private hands. A former NASA investigator named Joseph Gootens, who later became known for tracking down lost lunar artifacts, began searching for it in the 1990s. Gootens launched a covert operation he called Operation Lunar Eclipse, posing as a wealthy buyer seeking moon rocks. Through a trail of false companies and electronic correspondence, he traced the Honduras sample to a man in Florida. That man had received it from a former American diplomat who had kept it as a personal souvenir. For years it sat unnoticed in a garage sealed in a box, gathering dust, a fragment of another world, treated like an old trophy. When authorities finally recovered it, they confirmed its authenticity, a real piece of lunar basalt collected in 1972. by Apollo 17 astronauts Eugene Cernan and Harrison Schmitt. Its journey had taken it from the Taurus Littrow Valley on the Moon to a presidential ceremony in Honduras, and then to a suburban American storage box. And this was not the only one. Moon rocks have appeared in the strangest of places. One turned up mislabeled in a museum drawer, another surfaced in an estate auction of a diplomat. Some vanished from government buildings during times of upheaval. Their rarity has turned them into a kind of black market currency, a relic of the space age, traded like treasure. A single gram of moon rock can fetch over $5 million, depending on its history. Because NASA forbids private ownership of Apollo-collected lunar material, any such piece in civilian hands is considered illegal, yet collectors continue to pursue them. International investigations and volunteer recovery teams still work to trace and reclaim these artifacts. Why does this matter? Because these rocks are not mere souvenirs. They are archives of the cosmos, holding evidence of the moon's evolution, the Earth's origins, and the early history of the solar system. Losing one is not just unfortunate, it is a real scientific loss. Every moon rock is unique. Across all Apollo missions, only 382 kilograms were brought home. That is a tiny amount compared to the Martian meteorites and asteroid samples we collect today. These fragments are rare, delicate, and priceless. The rediscovery of one in a dusty garage reminds us how easily the extraordinary can fade into the ordinary when we stop paying attention. Something that once voyaged across the void, gathered by astronauts encased in suits worth millions of dollars, now rests quietly beside lawnmowers and toolboxes. It reminds us how the passage of time alters our sense of wonder. What was once humanity's crowning triumph gradually slipped into memory until someone decided to open the box again. Inside, a rock waited. Just a rock, but not quite. It was the moon itself. When we imagine the lunar surface, we often picture a flat, colourless desert of dust and craters. Yet if you look closer, truly look, you will see mountain ranges, immense peaks, and rugged highlands rivaling Earth's most dramatic landscapes. Some even soar higher than the Rocky Mountains, rising from the ancient crust as relics of an age when the solar system was fierce and untamed. Let us begin with the fundamentals. The moon no longer has tectonic plates or volcanic activity. It knows no wind, no rain, no erosion. So how does it possess mountains? The answer lies in impact. Unlike Earth, where mountains are sculpted by tectonic forces and collisions between plates, the moon's peaks were created through violence from the cosmos. Billions of years ago, gigantic asteroids and early planetary fragments slammed into the lunar surface with almost unimaginable force. These collisions hollowed vast basins, and the shock waves raised mountainous rims around their edges. Imagine dropping a stone into soft clay, the splash frozen into jagged shapes. One remarkable example is the Montes Rumker, a dome-like massif in the moon's northwest. Even more striking is the Montes Apenninus, a rugged range curving along the border of the Imbrium Basin, one of the largest and oldest impact scars on the moon. This range stretches for more than 600 kilometers, with peaks climbing to about 5,000 meters, 16,400 feet high. Peaks on the moon taller than the Rockies, whose highest points in Colorado reach roughly 4,400 meters, 14,400 feet. Another colossal summit, Mons Huygens, stands as the tallest mountain on the moon, rising to 5.5 kilometers, 18,000 feet taller than Mount Rainier, Mount Whitney, or any peak in the lower 48 states. Mons Huygens towers above the plains like a frozen wave, the remnant of a cataclysm that shook the lunar crust to its depths. Then there is Mons Hadley, located near the Apollo 15 landing site. This magnificent mountain rises around 4.5 kilometers, 15,000 feet above the surrounding terrain. When astronauts David Scott and James Irwin landed nearby, they described it as absolutely breathtaking, a sheer wall of grey stone rising against the black sky like a fortress from another world. Yet here is the paradox. Though the moon's mountains are tall, they do not appear so when you stand before them. Why? 2 reasons. First, the absence of atmosphere means no haze, no clouds, no gradual fading of distance. Everything appears crystal sharp, regardless of how far away it is. This clarity collapses depth, making enormous mountains seem deceptively close, their scale almost flattened. Second, the moon's gravity is only 1/6 that of Earth's, so while a peak might look imposing from orbit climbing, it would feel far less demanding. There is little gravitational resistance, no thin air, no oxygen loss, and no struggle against Earth's pull. You would bounce gently upward rather than trudge. Yet these are not mere curiosities. They are time capsules, geological museums, preserving the moon's ancient materials untouched by erosion. Some of the rocks found at higher altitudes are over 4 billion years old, remnants of the original lunar crust. Studying them could reveal how the moon was born, and in turn how Earth itself came to be. Future missions, robotic and human alike, are already being designed to explore these highlands, not only for science but also for potential resources. Certain mountain regions receive nearly endless sunlight, making them ideal for solar energy systems. Others may harbour exposed minerals, oxygen-rich regolith, or even hidden reserves of ice. So yes, the moon has mountains, vast awe-inspiring monuments forged in cataclysm, frozen in time for billions of years. Mountains that dwarf imagination that loomed above the Apollo explorers and may one day become outposts, observatories, or gateways to deeper space. We often picture the moon as silent and still, yet its mountains tell a story of fire and fury, of collisions that shape worlds. The scars remain, so do the summits, and perhaps one day we will stand upon them. When you gaze up at the moon on a clear night, you will notice dark shapes scattered across its face, broad, smooth plains contrasting with the lighter, cratered highlands. They form the familiar man in the moon, or the rabbit, depending on your culture's imagination. But these shadows are no illusions. They are real geological formations, immense ancient lava seas known as Maria, pronounced Maria. The name originates from the Latin word for seas because when early astronomers in the 1600s peered through their simple telescopes, they believed those dark regions were vast oceans. Only centuries later did we understand that they are not waters at all, but plains of solidified basalt born from immense volcanic eruptions billions of years ago. They tell the tale of a moon, once alive with heat and motion, far more turbulent than the silent orb we see today. Most of the lunar surface consists of highlands, rugged, ancient, mountainous terrain, bright and scarred by countless craters reflecting sunlight back toward Earth. Yet, about 16% of the moon's face is covered by the Maria, those smoother, darker expanses, mostly on the side that always faces us. They are lower in elevation and composed of basalt, the same rock that forms Earth's oceanic crust, and volcanic islands. But how did they form? It began with impacts on a scale almost beyond comprehension. Between 3 and 4 billion years ago, during what scientists call the Late Heavy Bombardment, asteroids and protoplanets struck the moon with extraordinary force. These colossal impacts excavated vast basins, some hundreds of kilometers across. The shock shattered the crust-opening fractures, through which molten rock from deep within could rise to the surface. Then came the floods, not of water but of molten fire. Lava surged from fissures, spreading slowly across those impact basins in thick glowing sheets, filling them like syrup poured into a hollow. Over time the lava cooled and solidified into the smooth basalt plains we now call the Maria. Frozen seas of once liquid stone, still and dark, their surfaces eerily flat compared with the chaotic terrain surrounding them. Astronomers, moved by poetry and imagination, gave them names that still echo with mystery. Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 touched down. Mare Imbrium, the Sea of Rains, one of the largest impact basins in the solar system. Mare Serenitatis, the Sea of Serenity. Mare Crisium, the Sea of Crises. Oceanus Procellarum, the Ocean of Storms, largest of them all. Despite their names, these seas have never held water. They are dry, solid and cold, but long ago they pulsed with molten energy, reshaping the moon's surface. Unlike Earth, whose crust is endlessly recycled through the motion of tectonic plates, the moon's lava seas froze where they lay, preserved for billions of years. When you look up at the lunar face tonight, you see a geological memory, a record of ancient volcanic violence, untouched by time. The basalt that forms the Maria differs from the rocks of the highlands. It is denser, darker, richer in iron and titanium, which is why it reflects less light. Some regions even contain glassy textures born when lava cooled so quickly that crystals could not form. Samples brought back by Apollo missions sometimes reveal this glass under the microscope, shimmering like tiny fragments of lunar obsidian. There is also an asymmetry, a quiet mystery. Most of the Maria lie on the near side of the moon, while the far side, though equally cratered, has almost none. The reason remains uncertain. It may be that the crust on the near side is thinner, allowing magma to erupt more easily, or that radioactive elements were distributed unevenly, generating localized heating beneath the surface. Whatever the cause, this imbalance left the moon with two distinct faces, one smooth and familiar, the other rough and hidden. Today, the Maria rank among the flattest places in the entire solar system, which is why they were chosen as the landing sites for Apollo missions, safe, level, and rich with geological history. The astronauts who walked there, quite literally, stood upon the moon's cooled blood, the last expression of a heart once molten and alive. Yet the story is not over. Scientists suspect these ancient plains still hold secrets, trapped gases, volatile minerals, perhaps traces of water bound within the rock itself. They study them to understand how worlds lose their heat, how magma behaves in low gravity, and how crusts fracture and evolve without tectonic renewal. So those dark shapes we see from Earth are not decorations. They are scars, frozen oceans of fire, remnants of a moon that once burned with internal fury. The next time you gaze upward and trace that pale face, its eyes and shadows and quiet smile, remember that you are looking at seas of lava older than any mountain on Earth, watching us as they have for billions of years. We have sent humans there, left footprints and flags, and brought fragments of that ancient world back home. Yet one of the most enduring instruments left behind, still working silently after all this time, is something small and simple, the retroreflectors. They do not draw attention, but they continue to connect our world to that distant, silent companion in the sky. No solar panels, no antennas, no blinking lights. Only small panels of mirrored prisms, each no larger than a suitcase, resting silently upon the grey dust of the lunar surface. Yet these humble instruments are part of the longest continuous scientific experiment in the history of space exploration. Since the year 1969, they have been reflecting laser beams back to Earth, and even now they continue their quiet conversation across space. A retroreflector is a marvel of elegant simplicity. It is composed of corner cube prisms, 3 mirrors arranged at perfect right angles, designed to return light precisely to its source, regardless of the angle from which it arrives. It works much like the coating on road signs or the reflectors on bicycles, but refined to an extraordinary degree for the vacuum of space. NASA placed these retroreflectors on the moon during the Apollo 11, Apollo 14, and Apollo 15 missions. The Soviet Union added 2 more through its robotic lunar programs. In total, 5 retroreflectors were set upon the lunar surface between 1969 and 1973. Their purpose was to measure with astonishing accuracy the distance between the Earth and the Moon, accurate to within a millimeter. The method is both poetic and precise. Scientists on Earth direct an immensely powerful laser toward one of these silent mirrors. The beam travels through the atmosphere, crosses the void, and strikes the Moon. The retroreflector sends the light back, and detectors on Earth record the exact time it takes for the pulse to complete the round trip, around 2.5 seconds. Multiply that duration by the speed of light, divide by 2, and you have the precise distance to the Moon. This is done every single day. And every single day, those quiet, mirrored boxes on a lifeless world reply. Through this experiment known as lunar laser ranging, we have learned things that once seemed beyond reach. The Moon is gradually moving away from Earth by about 3.88 centimeters each year. It seems negligible, yet over millions of years it will subtly reshape the length of our days. These measurements have even tested Einstein's general theory of relativity, confirming that gravity, motion, and time behave exactly as he predicted. The experiment has refined our understanding of the Moon's orbit, Earth's wobble, and even the delicate shifts in the Moon's rotation, all essential for navigation, climate models, and planetary science. What makes it even more remarkable is endurance. The reflectors continue to function flawlessly after more than half a century in space. They have endured temperature extremes ranging from minus 215 to plus 250 degrees every lunar day. They have survived radiation, micrometeorite strikes, and the constant settling of lunar dust. Yet, when lasers are aimed at them from observatories in Texas, France, and elsewhere, the signal still returns. It is not simple. The laser beam spreads as it travels, so by the time it reaches the Moon, it is roughly 2 kilometers wide. When it reflects back, only a few photons, perhaps 1 per second, reach the detector. Capturing that whisper of light requires precision, patience, and exquisite timing, but it works. Beyond its scientific utility, the retroreflector stands as a quiet emblem of human ingenuity, a symbol of how a small, unassuming object can endure beyond the ambitions that placed it there. The Apollo landers are silent. The flags have been bleached pale by radiation. The astronauts have long since returned to dust. But the mirrors remain, still responding, still speaking across the darkness. In recent years, scientists have noticed a decline in their efficiency, perhaps caused by dust lifted by micrometeorites or the cycles of lunar heat. This has inspired a new generation of improved retroreflectors designed to resist dust and extreme temperatures that will soon be carried by NASA's Artemis missions and private lunar landers. These will form a broader network across the Moon, expanding this quiet experiment's reach. And why continue? Because even now there is more to learn. These new instruments could help detect moonquakes, monitor gravitational variations, and one day provide navigation systems for future lunar explorers. Imagine it, a silent mirror resting untouched on a cratered plain, still speaking through light, still whispering data across the vacuum. No power, no moving parts, only geometry and physics perfectly aligned. It is among the most beautiful things we have ever achieved, to leave behind a small fragment of ourselves on another world with a purpose so pure, so precise, that it continues its task half a century later. So the next time you lift your gaze toward the Moon, remember this: it is not only reflecting the light of the Sunday. Somewhere up there, a fragment of human curiosity is reflecting our own light back at us, quietly, faithfully, still saying, "I am here." And though the Moon may seem silent and barren, it is not without order. You cannot simply fly there, plant a flag, and claim it as your own. That belongs to the realm of fiction. In reality, the Moon is governed by something profoundly human, a treaty, an agreement forged among nations to ensure that this celestial neighbor remains in spirit at least a place of peace. The notion that humanity might one day require laws for the Moon can seem peculiar, given that only a few people have ever walked upon its surface. Yet even in the 1950s, as the idea of space travel began to drift from imagination into reality, world leaders saw a possibility both wondrous and perilous. Without agreed rules, the cosmos itself could become the next arena of conflict. So in 1967, the Outer Space Treaty was created. Its full title, the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, including the Moon and other celestial bodies, may sound cumbersome, but it remains one of the most remarkable milestones in international law. It emerged in the depths of the Cold War, when the United States and the Soviet Union were locked in a fierce competition for dominance beyond Earth. And yet both sides shared one conviction: that the Moon must not become another front in humanity's divisions. The treaty was first signed by the United States, the Soviet Union, and the United Kingdom, later joined by more than 110 nations. It drew lines in the dust of the lunar surface. No country could ever claim ownership of the Moon. A flag, no matter how proudly planted, did not make it yours. The Moon and all celestial bodies were to be used only for peaceful purposes. Weapons of mass destruction were strictly forbidden both in orbit and on the lunar surface. All activities were to be carried out transparently and cooperatively. Every nation would bear responsibility for its actions in space, whether performed by governments or private enterprises. If a spacecraft or astronaut fell into distress, others, even rivals on Earth, were bound to help. In spirit, the moon belonged to no one, and therefore to everyone. But as decades passed, that idealistic vision grew tangled in complexity. In 1979, a new proposal arose, the Moon Agreement. It sought to expand upon the Outer Space Treaty, declaring lunar resources the common heritage of humankind. It imagined a future where the benefits of exploration and mining would be shared equitably among all nations, especially those still developing. Yet almost none of the major spacefaring powers accepted it. The United States, Russia and China all declined. Only 18 nations have ratified the Moon Agreement, none possessing the means to send humans to the lunar surface. The reason was simple. Space had become commercial. Private enterprises such as SpaceX and Blue Origin began to see the moon not merely as a symbol of exploration, but as an opportunity, a source of water, metals and energy. The notion of shared inheritance clashed with economic ambition. And so in practice, the Outer Space Treaty remains the primary framework that governs lunar activity, yet it is filled with ambiguities. It forbids owning land, but says little about extracting resources. It bans militarization, but is silent about defense systems or surveillance satellites. It calls for cooperation, yet offers no guidance for disputes. What happens if two nations attempt to mine the same crater? In 2020, the United States introduced the Artemis Accords, a non-binding set of principles designed to promote responsible lunar exploration. Those who sign agree to share scientific data, protect historic sites such as the Apollo landing zones, and avoid confrontations over resources. More than 40 nations have joined so far, though Russia and China have not. The result is a curious and fragile legal landscape, an ancient treaty from an era before mobile telephones, held together now by goodwill and voluntary agreements, while a new race unfolds. This time it is not for flags, but for water, minerals and energy. And this moment matters profoundly. The moon is awakening once more. The National Aeronautics and Space Administration plans to return humans to its surface within this decade. China has its own ambitions, envisioning a base near the South Pole. Private companies prepare to send landers, drills and habitats. All of them are heading for the same precious regions, craters cloaked in shadow rich with frozen water and sunlit ridges ideal for solar power. But what happens when two crews reach the same ground? Who decides who stays? Who owns the materials brought back to Earth? At present, there are no definitive answers. The laws we rely upon reflect a gentler age, hopeful, cautious, and idealistic. Their authors never imagined a world where entrepreneurs would send rockets to the moon, or where nations would speak openly of mining rights among the stars. Yet those same laws remain the bedrock of space governance today. So yes, the moon is protected by a peace treaty, by several in fact, and for over half a century they have kept it free from weapons, borders and war. But the next half century will test that harmony. The moon may belong to no one, but soon everyone will reach for a part of it. When you gaze up at the moon full and radiant, it appears as a perfect sphere, serene and balanced, like a pearl adrift in the night. But that is an illusion. In truth, the moon is misshapen, swollen, uneven and slightly off-center. Its form has been sculpted not only by gravity but by ancient forces long vanished, leaving it forever lopsided and subtly tilted. Gravity draws any large celestial body toward roundness, pulling its mass inward over time. Yet in the cosmos, perfection is rare. Even the roundness of the moon, like all worlds, carries the imprint of its turbulent past. Earth, for instance, is gently flattened at its poles and slightly swollen around the equator, a result of its steady rotation. The moon, however, turns far too slowly to form such a bulge, yet it holds its own peculiarities. Perhaps the most fascinating is that its mass is not distributed evenly. Its center of mass is displaced by roughly 2 kilometers toward Earth, making the side that faces us ever so slightly heavier. We cannot see this imbalance from here, but it has deep consequences. It helps explain why the moon always shows us the same face, rather than spinning a changing vista before our eyes. It is tidally locked, its uneven mass anchoring it into this orientation like a coin settling on its heavier edge. Even more curious, the lunar crust is thinner on the side that faces Earth. On average, that near side is around 20 kilometers thinner than the far side, and it carries more lava plains, more volcanic scars, and higher concentrations of radioactive elements such as uranium and thorium. This is why the side we know so well appears dark and marbled, filled with ancient lava basins, while the far side is brighter, rougher, and more heavily cratered. The reason for this great asymmetry remains uncertain, though scientists have proposed a few possibilities. One is that early in the Moon's history, Earth's immense heat influenced how it cooled. In those fiery beginnings, when the Moon was still a molten globe of magma after a colossal collision, the side facing Earth would have been constantly bathed in radiant warmth, while the far side cooled more swiftly. That uneven cooling may have left the crust thinner and changed the chemistry deep within, locking in a permanent imbalance. Another idea suggests that the Moon once had a smaller sibling, a companion world, that eventually collided and merged with it. Such an impact might have smeared extra material across one hemisphere, reshaping the surface and leaving behind the uneven structure we measure today. Whatever the cause, the outcome is undeniable. NASA missions have detected gravitational anomalies that match these irregular patterns of mass. Some are known as mass concentrations or mass cons, regions where buried dense material tugs more strongly on passing spacecraft. The Apollo missions had to adjust their trajectories to account for these subtle pulls, and modern orbiters still do the same. In simpler terms, parts of the Moon's gravity are stronger than expected because of what lies hidden beneath its surface. And the Moon's shape itself tells a similar story. If we could somehow smooth away every crater and mountain, the Moon would still not be a perfect sphere. It would remain slightly elongated in the direction of Earth, stretched like a soft balloon gently pulled by our planet's gravity. The distortion is only a few kilometers, but it is real, and the Moon has preserved that shape as it has slowly drifted away over billions of years. So while it seems a flawless, polished pearl suspended in the night sky, the Moon's reality is far from perfect symmetry. It is a world with a skewed gravitational field, a thinner volcanic near side, a thicker battered far side, and a core displaced from its center. A cosmic imbalance frozen in time. This lopsided form, though subtle, has guided how the Moon evolved, how it orbits, how it interacts with Earth, and how humanity designs missions to explore it. Understanding this strangeness helps reveal the processes that shape planets, the pull of tides, and even the hidden story of our own world. And when you look up and see that glowing disk, remember that it is an illusion of light. The Moon is not symmetrical. It is not even centered. It has been stretched, struck and pulled into its current form, a relic of ancient violence, shaped by gravity, lava, and the slow work of time. It may seem calm and perfect, but beneath that calm face lies a distorted remnant of creation, still gazing back at us with the same strange expression it has worn for billions of years. When we picture the Moon, we imagine a barren, airless, frozen desert flooded with sunlight, a place where no known life could endure. It is the very definition of a dead world. And yet a question lingers that scientists cannot quite silence. Could we have carried life there ourselves? During the Apollo missions, despite the utmost care, it is entirely possible that tiny Earth microbes found passage aboard those spacecraft. And in at least one instance, they may have survived. Let us go back to 1967, 2 years before the first humans landed. NASA was racing toward the Moon, and no one yet knew whether it might harbour its own microscopic life. If astronauts returned with lunar dust, could it contain alien pathogens? Might it contaminate Earth's fragile biosphere? These were genuine fears, strong enough that early Apollo crews were quarantined for weeks upon their return. But perhaps contamination worked the other way. Consider Surveyor 3, an unmanned probe that landed in 1967, sent ahead to study the lunar soil before any human footsteps arrived. Fast forward to 1969, Apollo 12 astronauts Charles Pete Conrad and Alan Bean touched down a mere 183 meters from the aging Surveyor spacecraft. In one of the most daring and intellectually fascinating moments of the mission, they walked across the lunar surface to meet that silent machine, documenting it in photographs and collecting fragments among them, a television camera and a circuit board to bring back to Earth. Their goal was simple yet profound: to understand how human-made instruments endure years in the unrelenting lunar environment. But when those relics were examined within the sterile walls of the Johnson Space Center, scientists encountered something astonishing. Inside the equipment was a living colony of bacteria. The organism was Streptococcus mitis, a microbe usually found within the human mouth and throat. Somehow it seemed to have survived 2 years of exposure to lunar vacuum radiation and extreme temperature shifts, and it was still alive. The revelation stunned the scientific community and dominated headlines. How could a microbe incapable of surviving mild dryness on Earth persist in the void of space? Had it fallen into a state of suspended animation, only to awaken upon return to the lab? For a time it appeared humanity might have unknowingly sent life to the moon. A tiny case of accidental panspermia. Yet, as decades passed, skepticism grew. Many researchers later argued the evidence was flawed. The surveyor components had not been opened in a perfectly sterile vacuum. They had been retrieved by astronauts, handled, and possibly contaminated during recovery. Even the laboratory's seals were imperfect. What was thought to be a lunar survivor could have been an earthly stowaway introduced through a breath, a touch, or a fragment of dust on a lab coat. The truth remains unresolved. Still, whether or not that particular bacterium endured on the moon, others might have. During the Apollo era, sterilization was rigorous but incomplete. Spacecraft were baked, scrubbed, and vacuum treated, yet no method was flawless. Some terrestrial microbes might have made the journey hidden within camera housings, flagpoles, hatch seals, or the fabric of a spacesuit. Bacteria are astonishingly adaptable. Certain species can persist as dormant spores for years, shielded by thin layers of metal, dust, or plastic. And within the moon's shadowed craters, lava tubes, or buried regolith, there may be pockets stable enough to preserve them longer than we can imagine. Modern experiments aboard the International Space Station have revealed that some microbes and even tardigrades can endure the harshness of space, its vacuum, radiation, and freezing cold, if afforded even minimal protection. The European Space Agency's exposure missions have demonstrated colonies surviving months outside the station's hull, shutting down their metabolism entirely before reawakening later as if nothing had happened. So could microscopic traces of Apollo still cling to the lunar surface? Quite possibly. That is why planetary protection has become a central concern in today's exploration of the cosmos. NASA and other agencies enforce strict protocols for missions to Mars, Europa, Enceladus, and even certain regions of the Moon, anywhere that might harbour or one day support life. Because once Earth's biology contaminates another world, there is no turning back. It raises a profound question. If we discover life beyond Earth, how can we be certain it is truly alien and not something we brought ourselves? As exploration accelerates with Artemis missions, SpaceX landers, and plans for international lunar bases, these questions grow ever more urgent. Should we attempt to cleanse the moon of our biological footprints, or has that moment already passed, with Apollo's microbes quietly marking our presence in lunar dust? Perhaps some survived, perhaps none did. Yet the question itself reveals something beautiful. The moon is not merely a rock orbiting in silence. It is a witness, a stage upon which we have already begun to leave more than footprints. When we speak of the moon, we often imagine its story as complete. Humans have landed 6 times, returned samples, left rovers and flags, mapped and studied its surface for decades. Surely we know it all. But that assumption could not be further from the truth. We have explored only a fraction of the lunar world, a span smaller than a single city on Earth. The rest remains untouched, untested, and profoundly unknown. And within that vast, silent frontier, the questions of life, contamination, and cosmic legacy continue to wait for us. The surface of the moon spans roughly 38 million square kilometers, about the same as the continent of Africa. It is vast beyond measure. Yet between the years 1969 and 1972, the Apollo astronauts explored no more than 93 kilometers in total, both on foot and using their lunar rovers. All 6 missions landed within the equatorial zone on the near side, each site chosen for its relative flatness and the safety it offered. The Apollo 11 crew ventured only a few hundred meters from the lunar module. Apollo 12 traveled a little farther to study the old Surveyor 3 probe. With Apollo 15, 16 and 17 came the rover's vehicles that extended their range, but even the longest journey covered only about 35 kilometers. That distance represents the sum of human travel across the moon, joined now by robotic missions. Although these robotic explorers have come from the United States, the Soviet Union, China, India and others, their reach remained small. The Soviet Lunokhod rovers traveled only a few dozen kilometers. China's Chang'e 3 and Chang'e 4 missions touched down on the near side and the far side respectively, each exploring a tiny fraction of terrain with their U-2 rovers. India's Chandrayaan 3 achieved a soft landing in the year 2023 near the lunar South Pole, but again it moved only a short way. Even when we combine every lander orbiter and sample return mission, the total area physically visited is almost negligible. More than 99.99% of the lunar surface remains unseen and untouched by any human or robot. This matters deeply. The moon is not a dull repetition of grey dust and stone. It is a world of variety shaped by time and cosmic violence. Its crust changes in composition, texture and age from one region to another. There are ancient volcanic domes, sinuous ridges that mark collapsed lava tubes, enormous basins buried beneath eons of debris, and places rich in rare minerals, helium-3, and perhaps even frozen water. We have only grazed the surface of this hidden diversity. Take the lunar South Pole, for example, a place of great scientific allure. Within its deep, permanently shadowed craters may lie billions of tons of water, ice preserved for billions of years, remnants of ancient comets or primordial condensation. This region could power the future of exploration, offering sunlight for energy and ice for fuel. Yet no human has ever set foot there. Not once, not even close. Or consider the far side of the moon forever turned away from Earth. It remained unseen until 1959, when it was first photographed. To this day, only one spacecraft has landed there, China's Chang'e 4 in 2019. What it revealed was astonishing, a landscape of thicker crust, fewer volcanic seas, and deep clues about the moon's inner composition that defy our existing models. Beneath the surface, there is mounting evidence of vast lava tubes, some so large that a city could fit inside. They may hold ancient water, untouched geology, or provide natural protection for future explorers. But no one knows. We will not know until we go. For all our technology and confidence, the moon remains largely a mystery. Most of what we understand comes from orbiters, remote sensing, and a few dozen kilograms of rock samples. As precious as those samples are, they all came from only 9 places, most within the same kind of terrain. Huge regions, from the rugged highlands to the volcanic plains and the strange magnetic anomalies, have never been sampled directly. In fact, when lunar meteorites are found on Earth, they often contain minerals unseen in any Apollo collection. That alone tells us the moon's geology is far more complex and varied than we once believed. So why have we not gone further? For decades, attention shifted elsewhere, to Mars, to deep space telescopes, to asteroids. The sense that we had already been there and done that made lunar missions difficult to justify. But that perspective is changing. NASA's Artemis program, China's expanding lunar ambitions, and the rise of commercial spaceflight have reignited interest in our nearest world. Artemis 3 intends to return humans to the South Pole within the next few years. A new wave of robotic explorers is now mapping landing sites, scouting resources, and preparing for human return. Private companies are developing landers to deliver instruments, infrastructure, and prospecting tools to untouched regions. The goal this time is not symbolic, it is systematic, because the moon is not simply a rock adrift in space. It is a record, a silent archive of the solar system's history waiting for us to read it. A museum preserving the early chronicles of our solar system, a bridge toward Mars, a living laboratory for discovery, and perhaps a vault of resources that may one day determine our survival among the stars. We have gazed upon it for tens of thousands of years, visited its edges, yet in truth, our exploration has scarcely begun. The moon is often imagined as pure and eternal, silent and untouched. But if you were to stroll across its surface, especially near the Apollo landing zones, you would find something unexpectedly human: litter. Not the kind that comes from candy or drink, but another form of debris born from science exploration and the unrelenting challenge of survival beyond Earth. Because humanity has left behind more than 400,000 pounds, over 180,000 kilograms of material on the lunar surface, nearly 200 tons of relics scattered across the dust. Much of it is not glamorous. Some was deliberately placed, some abandoned by necessity, and some simply left because returning it was never part of the design. Every Apollo mission faced the same unforgiving obstacle: weight. The greater the mass, the harder and costlier it was to escape Earth's gravity. That difficulty became even more pressing when the astronauts had to lift off from the lunar surface in the ascent stage of their lander. They needed to discard as much mass as possible to break free of the moon's pull and rejoin the command module waiting in orbit. The solution was simple and brutal: leave things behind. A great many things. Each Apollo landing left the descent stage of the lunar module, the gold-legged platform that served as the launch base, along with used scientific gear cameras, film canisters, empty fuel tanks, tools, extravehicular suits, and in the later missions, even entire roving vehicles. But the list goes further. Boots, backpacks, hammers, antennas, and even containers for urine were jettisoned. Yes, even that. In fact, nearly 100 sealed bags of human waste remain on the moon: feces, urine, and vomit, preserved in the vacuum of space. Each one left because every ounce mattered for liftoff. And not all this debris belongs to the Apollo era. Over the decades, dozens of robotic missions from the United States, the Soviet Union, China, India, Japan, and the European Space Agency have joined the lunar story. Many ended in deliberate crashes designed as impact tests or simply out of fuel. Others landed softly, deploying rovers or instruments, now long silent. Today, the lunar surface is marked with the remnants of these adventures: defunct orbiters, impact modules, shattered equipment, wheel tracks, broken probes, solar panels, antennas, fragments of glass, even 2 golf balls struck by Alan Shepard with a modified 6-iron club during Apollo 14. A small aluminium sculpture left on Apollo 15 stands as a quiet memorial to astronauts and cosmonauts who never made it home. Altogether, more than 800 known objects rest on the moon, from vast metal structures to tiny bolts and wires. Many lie undisturbed, unchanged for decades, with no wind or rain to erode them, no bacteria to decay them, and no vegetation to hide them. They remain exactly where humanity placed them. Some scientists argue these sites should be treated as heritage monuments, preserved like the ruins of ancient civilizations. They are not mere heaps of junk, but the fingerprints of one of humanity's most extraordinary achievements. Others see a more complex challenge. As we prepare for the next era of exploration, with the Artemis program, commercial landers, and international bases, the question grows urgent: what should we do with all this lunar waste? Should we clear it, recycle it, leave it untouched, or turn it into something new? Engineers imagine reusing the metals from old landers to build habitats or radiation shields. Researchers propose studying how plastics, glass, and alloys have weathered decades of cosmic exposure, offering lessons for future materials. Even the frozen waste could yield insight into how microbes endure space, or whether Earth life can persist in the lunar vacuum. Yet beneath all this lies a humbling truth. We carried our mess with us. Just as we have on the highest mountains and deepest oceans of Earth, we have left our traces on the moon. It is a quiet reminder that space travel, for all its grandeur, is also a story of logistics remnants and the art of leaving behind. The moon, that serene silver world we see in the night sky, is also a graveyard of tools, empty fuel tanks, and human waste. A museum of forgotten machines, a junkyard of progress, still expanding with every mission that touches down. With each new landing, it inherits a little more of our presence and a little more of our clutter. We know the moon is tidally locked to the Earth. It turns on its axis at exactly the same pace that it orbits us, which is why one face always looks toward our planet. That familiar landscape has watched over Earth for billions of years. Yet there is a thought, one that feels almost like science fiction, though it rests entirely within the realm of physics. One day the Earth itself could become locked to the moon. This phenomenon is called mutual tidal locking. It is not fantasy, but a genuine, if distant, possibility. In such a far future, not only would the moon forever show the same face to Earth, but Earth would forever show the same face to the moon. One hemisphere would always look upon the moon bathed in its eternal light, while the other would never see it again. How could such a thing come to be? It begins with the force behind it all, tidal friction. The moon's gravity tugs at Earth's oceans, drawing them into vast bulges of water. These are our tides. But Earth spins more quickly than the moon circles it. We rotate once every 24 hours, while the moon completes an orbit in 27.3 days. That difference means the tidal bulges are pulled slightly ahead of the moon in its orbit. That small offset creates a gravitational torque. The bulges pull forward on the moon, giving it the faintest push ahead. In doing so, energy is transferred from Earth's rotation to the moon's orbit. The consequence is extraordinary. The moon is slowly drifting away from us at roughly 3.8 centimeters per year. At the same time, Earth's rotation is losing speed, and our days lengthen by about 1.7 milliseconds each century. This process has unfolded for billions of years. When the moon first formed, Earth spun much faster. A day lasted only about 5 hours, and the moon was far closer in the sky. Over time, Earth's rotation slowed, and the moon drifted outward. If this continues without interruption, the two bodies could eventually reach a state where one Earth day equals one lunar orbit, that is, tidal locking. At that point, Earth and the moon would exist in a one-to-one spin-orbit resonance. From the lunar surface, Earth would stand motionless in the sky, never setting. From Earth, the moon would hang fixed over one part of the planet, unchanging, an eternal beacon above. The rest of the world would never see the moon again. Yet such an equilibrium lies far beyond our reach. It would take billions, perhaps tens of billions of years. Some estimates suggest over 50 billion years would be required for mutual tidal locking to occur, assuming nothing disturbs the process. But that assumption is vast because three great complications stand in the way. The first is the red giant phase of the sun. Long before Earth and Moon achieve this cosmic balance, the sun will exhaust its hydrogen and swell into a red giant. In about 5 billion years, it will expand dramatically, engulfing Mercury, Venus, and perhaps Earth itself. If our world is consumed or scorched into a barren rock, there will be nothing left for the moon to lock with. The second complication comes from gravitational disruptions. The Earth-Moon system does not exist in isolation. The pull of other planets, collisions with asteroids, or unimagined cosmic events could alter their paths. Over billions of years, even small disturbances accumulate, and no trajectory is truly secure. The third is that tidal effects themselves are not constant. The rate of slowing depends on the shape of our oceans, the movements of our continents, and the thermal state of Earth's interior. As the planet cools and its surface evolves, the efficiency of this energy exchange could change dramatically. Even so, as a thought experiment, mutual tidal locking reveals something profound. It reminds us that nothing in the universe is fixed. Orbits shift, rotations falter, and distances evolve. Every world changes across timescales so vast they defy human comprehension. If such a state were ever reached, what would life be like on a tidally locked Earth? On the hemisphere facing the moon, the view would be extraordinary. The moon would hover unmoving in the sky, vast and luminous, always full. On the far side, there would be endless darkness, the moon absent forever. Tides would stabilize, weather patterns would alter, and the Earth's once lively spin would become a graceful, synchronized dance with its ancient companion. But we will not be here to witness it. By then the sun will be a white dwarf, the Earth lightly gone, and the moon perhaps drifting through the silence of space. Still, the vision endures a moment in the deep future when our planet might turn once more toward its old friend and never turn away again. For as long as humans have looked upward, we have dreamed of the moon. Perhaps in time beyond imagination, the Earth itself will join that dream forever. Ancient civilizations once spoke of divine beings that ruled the moon of travelers who crossed the darkness to reach its glowing surface. Science fiction writers imagined shining domes and thriving settlements beyond the cradle of Earth. And now, for the first time in our history, those distant dreams are beginning to materialize. The moon is no longer just a destination, it is emerging as humanity's first home beyond our world. This is not an exaggeration. At this very moment, not in some distant future, but today, nations, private companies and space agencies are designing and building the first enduring human outpost on the moon. The motivation runs deeper than symbolism. The moon is the most practical gateway to life, beyond Earth, only 3 days' journey away, a mere step when compared to the long and perilous months required to reach Mars. It has a landscape gravity 1/6 of Earth's and a wealth of resources we are only beginning to comprehend. It is at once a laboratory, a proving ground, a crucible for survival, and perhaps a second home. Let us begin with what is already unfolding. The Artemis program, led by the National Aeronautics and Space Administration, is preparing to return humankind to the moon for the first time since the Apollo 17 mission in 1972. Yet this time the objective is not to visit and depart, it is to remain. Artemis 3, planned for the latter part of the 2020s, will target the lunar South Pole, a place where craters locked in eternal shadow hold billions of tons of frozen water. Water in space is everything. It can be consumed, it can sustain breath, it can be split into oxygen and hydrogen to fuel rockets. If we can extract it, we can endure. The long-term vision of the National Aeronautics and Space Administration includes the Gateway, a modular station orbiting the moon, and an Artemis base camp, a semi-permanent outpost upon its surface. The mission is to construct a functioning infrastructure, landers, power arrays, communication networks, laboratories, and eventually habitats capable of supporting long-term crews. But this endeavour is not theirs alone. China and Russia have announced plans for a shared international lunar research base, aiming to build facilities on the surface in the 2030s. SpaceX is developing its colossal Starship vehicle, intended to carry both cargo and humans to the moon and later onward to Mars. Private enterprises such as Blue Origin, Astrobotic, Intuitive Machines and Space are racing to deliver landers, rovers and experimental payloads, each step advancing both science and commerce. This is not fiction. It is real, and it compels us to confront a new question. What does it truly mean to colonize the moon? Unlike Earth, the moon has no atmosphere, no protective magnetic field, and no natural shield from radiation. Temperatures shift from scorching to freezing within a single day. Any future lunar settlement must be self-reliant and exceptionally resilient. Structures may need to be buried beneath the surface, perhaps within ancient lava tubes, to protect from radiation. They could be three-dimensional, printed from lunar soil to minimize transport from Earth, powered by solar panels on the illuminated ridges of the poles, and supported by robotic systems that mine, move and process essential materials. Life there would not resemble the comforts of cities on Earth. Astronauts would inhabit modular habitats, confined quarters with closed-loop systems, where every molecule of water, every fraction of energy, every breath of air is measured, recycled and preserved. It would be more like a submarine than a city, but the reward would be monumental. A working lunar base would alter the trajectory of human civilization. It could serve as a launch point for deeper exploration. A refueling station on the moon would drastically reduce the cost of reaching Mars or the asteroid belt. It would allow scientists to study the long-term effects of low gravity on the human body and mind. It would teach us how to live off the land of another world using what exists there instead of importing everything from Earth. It would even act as a safeguard and insurance policy for humanity should catastrophe strike our home planet. Most profoundly, it would be our first true test of settlement beyond Earth. How does one govern a world with no borders? Who owns its land and resources? What happens when people are born there, live their lives and grow old beneath an alien sky? When does a lunar base cease to be a research station and begin to become a civilization? These are not distant hypotheticals anymore. They are questions we must answer as we stand on the threshold of becoming a species of two worlds. Of course there will be risks. Radiation stands as one of the greatest challenges. Without the protective shield of Earth's magnetic field, the relentless rain of cosmic rays and solar flares becomes an ever-present threat. Any settlement on the lunar surface would need to be encased in formidable layers of protection. Then there are the micrometeorites, minuscule fragments of rock hurtling through space at speeds of tens of thousands of kilometers per hour, each one capable of piercing metal as if it were paper. Even the dust that coats the moon is treacherous, sharp, invasive, and clinging to everything it touches. But perhaps the more profound danger lies not in the physics, but in the psychology. The isolation, the confinement, the endless monotony of lunar existence could erode the human spirit, just as surely as radiation erodes metal. Yet we have endured worse. The effort to build a permanent presence on the moon will not be quick, nor will it be simple, but the groundwork is already being laid. Each lander that descends, each rover that crawls across the regolith, every mission that tests new systems, all of them bring us closer to transforming the moon from a destination into a location, a world with coordinates, with structures, with purpose. And one day, perhaps beyond our own lifetime, people may gaze up at that silvery sphere and whisper, "That is home." Not all of it, not yet, but a part of it, a beginning. For centuries, humanity has dreamed of lunar colonies. Now, for the first time, we are constructing them. To most of us, the moon remains a glowing disk hanging in the darkness, a poetic symbol, an unreachable idea. But to nations, to space agencies, to private companies, it has become something far more tangible, a strategic high ground. It is slowly becoming the front line of a new era in global space politics, a realm where science, ambition, resources, and diplomacy converge. The question is no longer simply whether we can go to the moon. It is about who will go, how they will go, what they will do once they arrive, and crucially, who will get there first. To understand this, we must look back. During the Cold War, the space race was a duel between two titans, the United States and the Soviet Union, locked in a battle of ideology and technology. The Apollo missions carried humans to the moon, but after those triumphs, the world turned away. For 50 years, the lunar surface lay untouched, politically dormant, a relic of an age of boldness. But that time has ended. The moon is once again a field of competition. Only now the players have multiplied. The United States, China, Russia, India, Japan, the European Union, South Korea, the United Arab Emirates, Israel, all are designing missions to return. Many of them are partnering with private companies, universities, and global alliances. What once symbolized prestige now represents power. There are many reasons. First, the resources. The moon holds minerals of immense value. Rare earth elements, titanium and helium-3, are potential fuel for the next generation of fusion reactors. Within its shadowed craters, billions of tons of water ice lie frozen, a treasure that could sustain life and create rocket fuel. Whoever gains control of those resources will hold a decisive advantage in the economics and logistics of space. Second, the moon's location. It offers an ideal launch pad for journeys deeper into the solar system. Its lower gravity means that launching from the lunar surface requires far less energy than from Earth. A nation that establishes infrastructure, their fuel depots, habitats, manufacturing facilities, will lead the next chapter of interplanetary exploration. And finally, there is influence. As more nations reach the moon, the power to write the rules of space becomes part of the reward. Yet those rules remain incomplete, uncertain. That brings us to the Artemis Accords proposed by the United States in the year 2020, an attempt to define the principles that will govern humanity's return to the moon. The Artemis Accords represent a declaration of intent, a set of guiding ideals crafted to ensure that humanity's return to the moon and our ventures beyond unfold peacefully. They call for openness, for nations to share their discoveries freely, to protect the fragile relics of our first steps, such as the Apollo landing sites, and to establish safety zones around areas of activity so that cooperation might prevail over competition. More than 40 nations have pledged their support, spanning Europe, Asia, and the Americas. Yet two significant powers, Russia and China, stand apart. They have charted their own path, envisioning the International Lunar Research Station, a shared base to be built in the 2030s. It is a competing vision shaped by a different balance of global influence, one that hints at the rise of two distinct space alliances reminiscent of the divided world of the Cold War. This is not open conflict, not yet, but it is undeniably a show of strength and intent. China's space program has accelerated with astonishing speed. It has landed on the hidden far side of the moon, returned precious samples, and now sets its sights on the lunar South Pole. Russia, slowed by economic strain, still holds a deep legacy in spaceflight. India, through its Chandrayaan 3 mission, touched down near the same pole, proving that it too is a capable explorer of the cosmos. Meanwhile, private enterprises from the United States and other nations are racing to deploy commercial landers prospect for resources and lay the foundations of lunar infrastructure. Yet beneath this surge of activity lies an unresolved question. The Outer Space Treaty of 1967, the cornerstone of space law, forbids any claim of sovereignty over celestial bodies. You cannot claim a crater. You cannot plant a flag and declare ownership. But the treaty says little about harvesting resources, establishing exclusive operational areas, or commercial exploitation. This absence leaves an enormous grey zone, a legal twilight where interpretation replaces clarity. So what happens when 2 missions target the same crater? Or when one nation constructs an outpost beside a shadowed deposit of ice that another seeks to reach? Who decides who stays, who moves, who has access? No rule exists to settle that dispute. And so the moon is transforming from a scientific destination into a stage for diplomacy and power. You can already hear it in the way leaders speak. The language has shifted, no longer about discovery alone, but about strategy, national presence, influence and control. Agencies are now designing lunar navigation systems, communication, constellations, and even frameworks for lunar internet and surveillance networks. What began as a pursuit of knowledge is slowly bending toward geopolitics among the stars. And as on Earth, what happens first defines what follows. The first nation to build, to sustain, to function will shape the rules. They will determine what is seen as normal, what is accepted practice, and others will inevitably follow their lead. The moon then becomes a proving ground for how we as a species will approach the rest of the cosmos. Will we unite, compete, share, or divide? Because make no mistake, the moon is no longer a silent, lifeless stone in the sky. It has become a realm of ambition, influence, creativity, and control. How we act there will determine how we reach Mars, how we touch asteroids, how we explore distant worlds. The moon remains ancient and serene, but beneath its silence, a distinctly human story is unfolding, a story of flags and laws, of pride and purpose. The moon is no longer merely a reflection of sunlight. It has become a reflection of ourselves.